Far above the noise of daily life there are worlds that never rest. Some are small and dense, their surfaces cracked and scarred, hiding vast oceans of molten metal below. Others are enormous, wrapped in endless clouds, where pressure turns gas into something stranger than liquid or solid. And beneath them all, unseen and unreachable, lie interiors that decide how a planet moves, how it ages, and whether it can ever feel familiar. From the outside, planets look calm, simple, complete. But the truth is quieter and far more complex. Inside every planet, materials are being sorted by gravity. Heat is slowly leaking away, and structures formed billions of years ago are still shaping what we see today. Some planets have solid ground all the way down. Others never offer a surface at all, and a few hide layers of matter that behave in ways found nowhere on Earth. Tonight is a slow journey inward, past clouds and crusts, through rock, ice and metal, into the hidden places that never see the light. Welcome to The Sleepy Scientist. If you enjoy calm, factual journeys like this one, please like the video and subscribe to the channel. And before we begin drifting inward, take a moment to say where you're watching or listening from. A planet's surface is the only part ever seen directly. It is where light reflects, where telescopes focus, where spacecraft land, and where photographs give the comforting illusion of familiarity. Craters, clouds, mountains, oceans. These are the features that shape intuition, and yet almost everything that makes a planet behave the way it does happens far below that visible skin. The surface is a consequence, not a cause. Beneath every planet lies an interior that quietly determines how that world evolves over billions of years. It decides whether volcanoes erupt or fall silent, whether a magnetic field shields the surface or fades away, whether an atmosphere clings tightly or is slowly stripped into space. Even the shape of the planet itself, whether it bulges, contracts or cracks, is written by forces deep inside. This creates a strange imbalance in how planets are understood. The most important regions are the ones that can never be seen directly. No drill has ever reached even a tiny fraction of the way to the center of a planet. On Earth, the deepest boreholes barely scratch the crust, a thin outer shell that makes up less than 1% of the planet's radius. Everything below that, the mantle and the core, is known only through indirect evidence. For other planets, the challenge is even greater. There are no seismic networks spread across Mars or Venus, no samples lifted from the core of Mercury, and yet scientists still speak with confidence about metallic cores, rocky mantles, molten layers, and buried oceans of exotic material. That confidence comes from physics. The first and most fundamental clue is mass. When a planet's mass is measured through its gravitational pull and its size is measured through observation, its average density can be calculated. Density immediately narrows the possibilities. A planet made mostly of rock will fall into one range. A planet rich in metal will be denser. A planet dominated by gas or ice will be lighter for its size. Even this simple calculation already reveals that planets are not uniform spheres. Something inside must be heavier than the outer layers, pulling mass inward. Gravity ensures that planets do not stay mixed. In the early stages of formation, when a planet is still hot from collisions and radioactive decay, its interior can partially or fully melt. When that happens, materials begin to separate by density in a process known as planetary differentiation. Heavy elements like iron and nickel sink toward the center. Lighter materials rise upward. Over time, this sorting creates layers. A dense core forms at the center. Above it sits a mantle of less dense rock or ice. On top, the lightest materials form a crust or atmosphere. Differentiation is not a minor detail. It is one of the defining processes that turns a collection of debris into a planet. Once layers form, they interact in complex ways. Heat trapped deep inside begins to move outward. If the interior is hot enough and the material can flow, slow convection currents form. These currents transfer heat upward and reshape the planet from within. On Earth, mantle convection drives plate tectonics, recycling crust and reshaping continents. On other planets, the same basic physics may exist but play out very differently, or not at all. The presence or absence of motion inside a planet has lasting consequences. A molten, moving core made of electrically conductive material can generate a magnetic field through a mechanism known as the Dynamo process. As liquid metal circulates, it creates electric currents, which in turn generate a magnetic field that extends far into space. That magnetic field can deflect charged particles from the Sun, protecting the atmosphere from erosion. Earth's magnetic field, generated by motion in its liquid outer core, is one of the reasons its atmosphere has survived for billions of years. Mars tells the opposite story. Evidence from orbiting spacecraft shows that Mars once had a global magnetic field. Today, it does not. The most likely explanation is that its core cooled too quickly. As the planet lost internal heat, the motion in its core slowed and eventually stopped. Without a sustained dynamo, the magnetic field collapsed. Over time, the solar wind stripped much of the Martian atmosphere away, leaving behind a cold, thin remnant. The fate of the surface was sealed by changes deep inside. Volcanism follows a similar pattern. Lava erupts not because a surface decides to be dramatic, but because heat and pressure build below. A planet with a hot, partially molten interior can feed volcanoes for millions or even billions of years. A planet that cools too quickly becomes geologically quiet. Its surface freezes in time, preserving ancient scars but offering little renewal. Even a planet's shape can betray its interior. Some worlds are slightly flattened at the poles and bulged at the equator. This happens because rotation interacts with internal structure. How much a planet deforms depends on how rigid or fluid its interior layers are. Subtle measurements of a planet's gravity field can reveal whether mass is concentrated toward the center or spread more evenly, offering another indirect glimpse beneath the surface. All of this means that planetary science is in many ways detective work. Instead of direct observation, scientists rely on multiple independent clues: gravity measurements from orbit, magnetic field strength and structure, subtle wobbles in rotation, seismic waves where available, laboratory experiments that compress materials to pressures millions of times greater than Earth's atmosphere, computer models grounded in fundamental physics. Each method alone is incomplete. Together, they form a coherent picture. The key point is that surfaces can mislead. Two planets can look similar on the outside and behave very differently because of what lies within. Venus and Earth are nearly the same size and bulk composition, yet their internal dynamics have diverged dramatically. One developed moving plates and a long-lived magnetic field. The other appears locked beneath a stagnant outer shell, slowly releasing heat in rare and catastrophic events. The difference is not cosmetic, it is structural. Other planets challenge intuition even further. Some have no solid surface at all, transitioning gradually from gas to liquid to something stranger as pressure increases. Others hide layers of material that behave unlike anything commonly encountered on Earth, where water and ammonia form exotic states under immense compression. In these environments, familiar categories like solid and liquid begin to blur. Understanding planetary interiors also places Earth in context. The planet beneath familiar feet is not the default outcome of planet formation. It is one example among many. By comparing Earth's interior to those of other worlds, scientists can identify which features are common and which are rare. This comparison sharpens understanding of habitability, stability, and long-term change. It also reveals how fragile certain conditions may be. Throughout this exploration, one principle remains constant. What happens inside a planet unfolds slowly. Interiors change over millions and billions of years. Heat leaks away at a patient pace. Materials shift and settle. Magnetic fields strengthen, weaken, or vanish. These processes rarely announce themselves loudly on human timescales. They operate beneath awareness, shaping outcomes long before they become visible. In that sense, planetary interiors are quiet architects. They build landscapes without ever being seen. They decide fates without spectacle, and they remind us that the most powerful forces in a planetary system often work far from the light, deep below the surface where pressure is high, temperatures are extreme, and change happens one careful step at a time. To understand planets, then, is not just to look outward, but inward. Standing on the surface of a planet, it is natural to assume that what can be seen is what matters most. Rock feels solid, ground feels permanent, and yet almost everything known about planetary interiors comes from places no one has ever visited, using signals that never show a picture, only numbers, patterns, and delays. Knowing what lies inside a planet is not a matter of looking, it is a matter of listening, weighing, and carefully interpreting how a world responds to invisible forces. The simplest clue comes from gravity. Every planet pulls on the space around it, and that pull reveals how much mass the planet contains. When that mass is compared to the planet's size, its average density can be calculated. Density immediately tells a story. A world that is small but heavy must contain a large amount of dense material, such as metal. A world that is large but relatively light must be rich in gas, ice, or low-density compounds. This single calculation already rules out countless interior possibilities. Density does not give a detailed map, but it sets boundaries. It tells scientists what a planet cannot be made of. Gravity does more than reveal mass. Subtle variations in a planet's gravitational field can expose how that mass is distributed inside. If a planet were perfectly uniform, its gravity would be smooth and predictable. In reality, gravity often varies slightly from place to place. These variations can be measured by tracking how spacecraft speed up or slow down as they pass overhead. Even tiny changes in velocity can be detected over time. From these measurements, scientists build gravity maps that hint at buried structures. Regions where mass is concentrated pull more strongly. Regions with lighter material pull less. On Earth, gravity maps reveal dense mantle structures and thinner crustal regions. On other planets, they reveal hidden basins, buried mountain roots, and deep internal layering. Rotation adds another layer of information. A spinning planet does not behave like a rigid object unless it truly is rigid throughout. Many planets bulge slightly at the equator due to rotation. The degree of that bulge depends on how mass is arranged inside and how easily interior layers can deform. By measuring a planet's shape and rotational behavior, scientists can infer whether its interior behaves more like a solid block or a layered system with fluid regions. This is where Earth becomes a reference world. Earth is the only planet where the interior can be studied directly through seismic waves. When earthquakes occur, they send vibrations through the planet. These waves travel at different speeds depending on the material they pass through. Some waves move through solids and liquids. Others cannot travel through liquids at all. By measuring when and where these waves arrive at detectors around the globe, scientists reconstruct a layered image of Earth's interior. In the early 20th century, this approach led to a remarkable discovery. While studying seismic wave arrivals, the Danish seismologist Inge Lehmann noticed that certain waves behaved in a way that could not be explained by a fully molten core. Her careful analysis showed that Earth must contain a solid inner core surrounded by a liquid outer core. This insight, published in 1936, fundamentally reshaped understanding of Earth's deep structure. Seismology reveals more than layers. It reveals temperatures, compositions, and even slow movement within the mantle. Convection patterns can be inferred from how seismic waves bend and slow. Earth's interior is not static. It flows, slowly but persistently over geological time. For other planets, direct seismology is rare but not absent. On Mars, seismic measurements from NASA's InSight mission detected Marsquakes and meteorite impacts. These signals provided the first direct evidence of the size and composition of the Martian core. The data revealed a core that is larger and less dense than expected, likely rich in lighter elements such as sulfur. Even with limited instruments and a short operational lifetime, seismic data transformed understanding of Mars's interior. Where seismic waves are unavailable, magnetic fields offer another window. A planet's magnetic field is not just a feature of space, it is a direct consequence of motion deep inside. Magnetic fields arise when electrically conductive material moves within a planet, typically liquid metal. The strength, shape, and stability of a magnetic field reveal whether a planet's core is molten, how vigorously it circulates, and whether that motion is sustained over long periods. Earth's magnetic field is strong and long-lived, indicating a liquid outer core with ongoing convection. Mercury has a weak magnetic field, suggesting a partially molten core despite its small size. Venus has no detectable global magnetic field, implying either a solid core, very sluggish motion, or a lack of conditions needed to sustain a dynamo. Mars preserves remnants of an ancient magnetic field locked into its crust, evidence that its core was once active but later cooled. Spacecraft measurements make these conclusions possible. Orbiters can measure magnetic fields directly as they sweep through a planet's surrounding space. They can also track subtle changes in spacecraft motion caused by gravity. Missions such as Juno at Jupiter and Cassini at Saturn use these techniques to probe deep into giant planets, revealing layered interiors, diffuse cores, and unexpected mass distributions. Jupiter, for example, was once thought to have a compact solid core. Gravity data now suggest a more diffuse region, where heavy elements are spread out over a large volume. This finding challenged earlier models and forced a revision of how giant planets form and evolve. Laboratory experiments complete the picture. Inside planets, pressures can reach millions of times the pressure at Earth's surface, and temperatures can exceed several thousand degrees. These conditions cannot be observed directly, but they can be recreated briefly in laboratories. Using devices such as diamond anvil cells and powerful lasers, researchers compress tiny samples of material to extreme states. By measuring how materials behave under these conditions, scientists determine which phases are stable deep inside planets. These experiments reveal surprising results. Water, under immense pressure, can enter a superionic state where oxygen atoms form a solid lattice, while hydrogen ions move freely. Metals may change structure. Common compounds behave in unfamiliar ways. Each result feeds back into planetary models, refining predictions about interior layers. Despite all this sophistication, certainty has limits. Planetary interiors cannot be observed directly. Models are built by combining many lines of evidence, each with uncertainties. Gravity data may allow multiple interpretations. Magnetic fields can weaken or strengthen over time. Laboratory experiments are constrained by scale and duration. Even seismic data depends on assumptions about composition and temperature. As a result, interior models are probabilistic rather than absolute. Scientists speak in terms of best fits, ranges, and likelihoods. A planet's core may be described as likely liquid, probably mixed with lighter elements, within a certain temperature range. These are not guesses. They are carefully constrained conclusions drawn from physics, observation, and comparison. This uncertainty is not a flaw. It is an honest reflection of distance and scale. What makes the process remarkable is how much can be known without ever seeing the interior directly. By listening to vibrations, tracking tiny motions, measuring invisible fields, and recreating extreme environments in laboratories, scientists assemble a coherent understanding of worlds that can never be opened. In planetary science, knowing what lies beneath is less about certainty and more about consistency. When gravity, magnetism, seismic behavior, and physical experiments all point toward the same conclusion, confidence grows. When they disagree, models evolve. In this way, planets reveal themselves slowly, not through images, but through how they respond to the fundamental forces of nature. Before a planet ever has a surface, it already has a history of heat. Long before continents, clouds, or craters exist, a young planet begins as a growing collection of material, orbiting a newly formed star. Dust grains collide, pebbles stick, larger bodies sweep up smaller ones. This gradual growth process is known as accretion, and it is far from gentle. Each collision releases energy. Each impact converts motion into heat. As material piles up, gravity squeezes the growing body tighter, adding still more warmth. In the earlier stages, a forming planet is less a solid object and more a hot, chaotic environment. Impacts are frequent. Orbits are unstable. The difference between a quiet accumulation and a violent collision can be a matter of timing. Some impacts add material smoothly. Others arrive at tremendous speeds, releasing enough energy to melt large portions of the planet. Accretion alone can raise temperatures dramatically. As a planet grows larger, its gravity strengthens, allowing it to pull in even more material. This creates a feedback loop. More mass leads to more impacts, which leads to more heating. For sufficiently large bodies, this process can melt the interior entirely, at least temporarily. Rock behaves like liquid. Metal separates and sinks. The early planet begins to reorganize itself from the inside out. But accretion is only the beginning. Even after the most violent phase of growth ends, planets continue to generate heat internally. One of the most important long-term sources comes from radioactive decay. Certain elements are unstable. Over time, they break down into more stable forms, releasing energy in the process. This energy appears as heat, and when enough radioactive material is present, it can keep a planet warm for billions of years. On Earth, radioactive decay from elements such as uranium, thorium, and potassium contributes a significant fraction of the heat flowing out of the planet today. This heat drives mantle convection, fuels volcanic activity, and helps sustain the conditions needed for plate tectonics. Without it, Earth would have cooled much faster, and its surface would look very different. In the earlier solar system, radioactive heating was even more intense. Short-lived radioactive isotopes played a crucial role during the first few million years of planet formation. One of the most important was aluminium-26. This isotope decays rapidly, releasing heat over a relatively short timescale. Although it no longer exists in meaningful quantities today, its presence in the early solar system is recorded in meteorites, which preserve chemical signatures of its decay products. The heat released by aluminium-26 was enough to melt small planetary bodies completely. Asteroids only tens or hundreds of kilometers across were able to develop molten interiors. Metal sank toward their centers. Rock formed mantles and crusts. Some of these bodies cooled and solidified quickly, freezing their internal structure in place. Others collided and were broken apart, scattering fragments that later fell to Earth as meteorites. These meteorites provide direct evidence that differentiation and melting occurred very early, even in small objects. For larger planets, early radioactive heating combined with accretional energy to produce deep magma oceans. Earth likely experienced one or more global melting events, where much of the surface and upper mantle were molten. During these periods, differentiation proceeded rapidly. Dense iron flowed downward to form the core. Lighter silicate materials rose upward. The basic layered structure of Earth was established early, even though it continues to evolve today. Internal heat, once generated, does not disappear quickly. How long a planet stays warm depends strongly on its size. Larger planets have a smaller surface area relative to their volume, which means they lose heat more slowly. Heat escapes through the surface, radiating into space. A small planet has a large surface compared to its interior, allowing heat to leak away quickly. A large planet holds onto its warmth much longer. This simple geometric relationship has profound consequences. Mercury, small and close to the Sun, cooled rapidly. Its interior solidified early, limiting long-term geological activity. Mars, larger than Mercury but still relatively small, cooled more slowly but eventually lost much of its internal heat. Earth, larger still, retains enough heat to remain geologically active billions of years after formation. Giant planets occupy an entirely different regime. Jupiter and Saturn are so massive that they retain enormous amounts of internal heat. In fact, both planets emit more energy than they receive from the Sun. This excess energy comes from a combination of residual heat from formation and ongoing gravitational contraction. As these planets slowly compress under their own gravity, they release additional heat, a process known as Kelvin-Helmholtz contraction. For Uranus and Neptune, the picture is more complex. Neptune emits significantly more internal heat than Uranus, despite their similar sizes. The reasons for this difference are still debated. It may involve differences in the internal layering, composition, or how efficiently heat is transported upward. What is clear is that internal heat does not behave uniformly, even among similar worlds. Heat shapes everything inside a planet. When interior temperatures are high enough, materials can flow. Solid rock behaves plastically over long time scales, slowly creeping rather than cracking. This allows convection to occur. Hot material rises, cooler material sinks. These motions transport heat outward and reshape the planet's interior structure. As a planet cools, convection can weaken or stop altogether. Once temperatures drop below certain thresholds, materials become too stiff to flow. Convection slows. Heat becomes trapped. In some cases, this can lead to a buildup of internal energy beneath a rigid outer shell. When that energy is eventually released, it may occur in rare but dramatic events, such as massive volcanic resurfacing episodes. Venus is often cited as a possible example of this behavior. Internal heat also controls whether a planet can generate a magnetic field. A magnetic field requires motion within an electrically conductive layer, usually a liquid metal core. If a planet cools too quickly, its core may solidify, shutting down this motion. Without sustained heat to drive convection, the magnetic field weakens and disappears. The planet becomes more vulnerable to interactions with its space environment. Throughout the solar system, the fingerprints of internal heat are everywhere. They appear in the folded mountains of Earth, the vast lava plains of the Moon, the ancient volcanoes of Mars, the powerful storms of Jupiter, and the surprising energy output of Neptune. In each case, what is visible at the surface reflects conditions deep below. Perhaps the most important insight is that internal heat is not a single process with a single outcome. It arises from multiple sources. It fades at different rates. It interacts with composition, size, and structure in complex ways. Two planets can start with similar amounts of heat and diverge dramatically over time. Others may begin differently and converge towards similar end states. Internal heat is the thread that connects planet formation to planetary evolution. It links the violent beginnings of accretion to the quiet persistence of geological activity billions of years later. It explains why some planets remain active while others become frozen relics. And it provides a unifying framework for understanding why planetary interiors matter at all. To understand what lies inside a planet, it is not enough to know what it is made of. It is necessary to know how warm it has been, how quickly it cooled, and how that heat has moved through its interior over time. Mercury looks small and unassuming from a distance, a scorched, cratered world clinging close to the sun. Its surface tells a story of extremes: days hot enough to melt lead, nights cold enough to freeze gases solid, a landscape battered by impacts and frozen in time. Yet the most surprising feature of Mercury is not written on its surface at all. It is buried deep inside. For a planet so small, Mercury is unexpectedly heavy. When scientists measure Mercury's mass and compare it to its size, the result is striking. Mercury is far denser than it should be if it were made of rock alone. In fact, its average density is only slightly lower than Earth's, despite being much smaller. The only way to explain this is with metal, a great deal of metal. Mercury's interior is dominated by an enormous iron-rich core that takes up an unusually large fraction of the planet's volume. Estimates suggest that the core may account for more than half of Mercury's total radius and around 70% of its mass. By comparison, Earth's core makes up closer to half of Earth's radius and about 1/3 of its mass. Mercury, in essence, is a metal planet with a thin, rocky shell wrapped around it. The mantle above that core is correspondingly thin. On Earth, the mantle is a vast region of slowly flowing rock thousands of kilometers thick. On Mercury, the mantle may be only a few hundred kilometers deep. The crust above it is thinner still. This extreme internal structure makes Mercury an outlier among the rocky planets and raises an obvious question. How did it end up this way? Several competing formation scenarios have been proposed, each with different implications for Mercury's early history. One idea is that Mercury formed normally, much like Earth and Venus, but later lost much of its rocky mantle. In this scenario, a massive collision early in the solar system's history stripped away large portions of Mercury's outer layers, leaving behind a metal-rich core. This idea is sometimes called the giant impact hypothesis for Mercury. similar in spirit to theories about the Moon's formation, but with a far more destructive outcome for the planet itself. Another possibility involves the early Sun. In the young solar system, the Sun was far more active than it is today. Intense solar radiation and powerful solar winds may have blasted away lighter materials from planets, forming very close to the Sun. Under this scenario, Mercury's proximity meant that much of its silicate material was eroded or vaporized, leaving behind a dense metallic remnant. A third idea suggests that Mercury simply formed from metal-rich material to begin with. The inner regions of the protoplanetary disk may have been chemically distinct, with metal grains surviving closer to the Sun while lighter compounds condensed farther out. If Mercury accreted from this metal-heavy reservoir, its large core may not require dramatic stripping events at all. Each hypothesis has strengths and weaknesses, and the true explanation may involve elements of more than one. What makes Mercury particularly valuable to scientists is that its interior still leaves measurable fingerprints on the surface. One of the most important sources of information about Mercury comes from the Messenger spacecraft, operated by NASA. Messenger orbited Mercury for several years, mapping its surface, gravity field, and magnetic environment in unprecedented detail. The data it returned fundamentally reshaped understanding of Mercury's interior. Gravity measurements from Messenger confirm that Mercury's mass is highly concentrated toward the center. The spacecraft also detected subtle variations in Mercury's rotation, known as librations. These small wobbles revealed that Mercury's outer core is at least partially molten. If the entire core were solid, the planet would rotate more rigidly. The observed motion indicates a liquid layer deep inside. This finding was unexpected. Mercury is small. Small planets are expected to cool quickly, and yet billions of years after formation, Mercury still retains a molten core layer. This lingering heat is enough to sustain another surprising feature, a magnetic field. Mercury has a global magnetic field, albeit a weak one. It is roughly 1% the strength of Earth's magnetic field, but it is unmistakably present. Measurements show that it is generated by a dynamo process within the planet's core, much like Earth's. Liquid metal is moving, electrical currents are flowing, and a magnetic field is being produced. This discovery was puzzling when first confirmed. Given Mercury's size, scientists expected its core to have solidified long ago. Instead, the planet appears to have retained enough internal heat to keep part of its core molten. Several explanations have been proposed, including the presence of lighter elements such as sulfur in the core, which lower the melting temperature and delay solidification. Mercury's magnetic field is also offset. Unlike Earth's field, which is roughly centered on the planet, Mercury's magnetic field appears shifted toward the north. This asymmetry may reflect uneven convection within the core or interactions between the core and mantle. It is another reminder that Mercury's interior is not only extreme but dynamically complex. The planet's surface bears visible scars of its interior evolution. As Mercury cooled over time, its large metal core contracted. Metals shrink as they cool and solidify. Because the core makes up such a large fraction of Mercury's interior, this contraction had dramatic effects. The planet's surface was compressed, leading to the formation of long, curved cliffs known as Labatt scarps. These scarps stretch for hundreds of kilometers across the surface and rise steeply above the surrounding terrain. They are essentially wrinkles formed as the planet shrank. Estimates suggest that Mercury's radius may have decreased by several kilometers as its interior cooled. No other rocky planet shows this phenomenon to the same extent. Earth's interior is buffered by mantle convection and plate tectonics, which recycle and reshape the crust. Mercury lacks these processes. Its thin mantle and rigid outer shell mean that when contraction occurs, the surface simply breaks and buckles. Tectonics on Mercury are therefore very different from those on Earth. There are no drifting plates, no spreading ridges, no subduction zones. Instead, Mercury's tectonic features are dominated by compression. The crust is pushed together, not pulled apart. Faults thrust upward. Old terrain is shoved over younger ground. The planet records its cooling history directly in its surface geometry. Despite its harsh environment, Mercury's interior also holds chemical surprises. MESSENGER detected higher than expected abundances of volatile elements on the surface, including sulfur and potassium. This finding challenged earlier assumptions that Mercury must have lost most of its volatile material due to its proximity to the Sun. Instead, it suggests that Mercury formed under conditions that allowed certain volatiles to survive, again complicating simple formation models. All of this paints a picture of a planet that defies easy categorization. Mercury is small yet internally active, metal-rich yet not stripped clean of lighter elements, magnetized yet weakly so. It cooled quickly, yet not completely. Its interior evolution followed a path distinct from every other rocky planet. In many ways, Mercury represents an extreme end member. By studying it, scientists test the limits of planetary formation theories. Any explanation that works for Earth, Venus, and Mars must also account for Mercury's unusual structure. Its oversized core forces models to confront how metal and rock were distributed in the early solar system, and how violent or gentle planetary growth truly was. Mercury also serves as a reminder that size alone does not determine destiny. Internal composition matters, heat retention matters, chemical makeup matters. A planet only slightly smaller than Mars could end up with an interior more metal-rich than anything else in the inner solar system. From the outside, Mercury appears simple. From the inside, it is one of the most complex worlds orbiting the Sun. Its surface tells the story of impacts and exposure. Its interior tells a deeper story of metal, heat, contraction, and persistence. And together, they reveal how profoundly a planet's inner structure can shape everything that comes after. Venus is often described as Earth's twin, and at first glance the comparison seems reasonable. The two planets are similar in size, mass, and overall bulk composition. Both are rocky worlds that formed in the inner solar system. Both likely began with molten interiors, metallic cores, and thick mantles of silicate rock. And yet, despite these similarities, Venus and Earth followed radically different paths. The reason lies deep inside. Based on its size and density, Venus almost certainly has a core made primarily of iron, much like Earth's. Surrounding that core is a thick mantle of rocky material, also broadly similar in composition to Earth's mantle. In terms of raw ingredients, Venus does not appear exotic or unusual. There is no obvious reason, from composition alone, to expect it to behave so differently. And yet it does. One of the most important differences between Venus and Earth is how heat escapes from the interior. On Earth, heat is transported upward through a system of moving tectonic plates. The rigid outer shell is broken into segments that slowly drift, collide, and recycle back into the mantle. This process, known as plate tectonics, allows heat to leak out steadily over long periods of time. Venus shows no clear evidence of this process. Instead of a mobile outer shell, Venus appears to have what scientists call a stagnant lid. The outermost layer of the planet behaves as a single unbroken shell. It does not fracture into moving plates. It does not sink back into the mantle. Heat rising from below has nowhere easy to go. This difference has profound consequences. In a stagnant lid system, heat builds up beneath the rigid outer layer. Over time, the mantle beneath becomes hotter and more buoyant. Pressure increases. Eventually, the system must release energy somehow. But without plate boundaries to act as outlets, that release may happen in rare, catastrophic episodes, rather than as a steady flow. This idea underpins one of the leading explanations for Venus's surface. The planet appears to have been resurfaced relatively recently in geological terms. Large regions show a scarcity of impact craters, suggesting that older terrain was erased and replaced. One hypothesis proposes that Venus undergoes episodic resurfacing events, where internal heat builds up for hundreds of millions of years and is then released in massive volcanic outpourings that cover much of the planet in lava. In this picture, Venus's surface is periodically reset. Rather than continuous recycling like Earth, Venus may experience long periods of relative calm punctuated by global or near-global volcanic episodes. These events would release enormous amounts of heat and gas into the atmosphere, dramatically reshaping both the surface and the climate. Interior heat and atmosphere are tightly linked on Venus. Volcanic eruptions release gases trapped inside the planet, including carbon dioxide and sulfur compounds. On Earth, much of this carbon dioxide is eventually removed from the atmosphere through weathering and plate tectonics, becoming locked away in rocks. Venus lacks these removal mechanisms. Once gases are released, they remain. Over time, this leads to accumulation. Venus's atmosphere is extraordinarily dense, composed mostly of carbon dioxide, with surface pressures dozens of times higher than Earth's. This thick atmosphere traps heat through the greenhouse effect. Sunlight enters, energy is absorbed, and heat struggles to escape. The result is a surface hot enough to melt lead, regardless of whether it is day or night. This runaway greenhouse effect is not simply an atmospheric accident. It is tied to the planet's interior evolution. As internal heat drives volcanism, gases are released. As the atmosphere thickens, surface temperatures rise. Higher surface temperatures reduce the efficiency of heat loss from the interior, because the temperature difference between the interior and surface decreases. This creates a feedback loop. Interior heat feeds atmospheric warming, and atmospheric warming slows interior cooling. Venus becomes trapped in its own heat. Another critical mystery lies at the planet's center. Despite its size and composition, Venus has no detectable global magnetic field. This is surprising. A planet with an iron-rich core should, in principle, be capable of generating a magnetic field if the core is molten and convecting. Several explanations have been proposed. One possibility is that Venus's core has largely solidified, eliminating the fluid motion needed to sustain a dynamo. Another is that the core is molten but lacks sufficient convection. Without a temperature difference driving motion, liquid metal can sit quietly, generating no magnetic field. A third possibility is that Venus once had a magnetic field that faded as internal heat flow declined. The absence of a magnetic field has consequences. Without a magnetic shield, Venus's upper atmosphere is directly exposed to the solar wind. Over time, this interaction can strip lighter gases away. This may help explain why Venus lacks water today, despite evidence that it may once have had more moderate conditions. Hydrogen escapes easily. Oxygen reacts with surface rocks. What remains is a dense, dry atmosphere dominated by carbon dioxide. Venus's mantle structure may also differ subtly from Earth's. Some models suggest that Venus's mantle may be more uniformly hot, with less vigorous convection. Others propose layered convection, where heat transport occurs in stacked regions rather than through a single large overturning system. These differences could influence how stress builds up beneath the crust and how volcanic activity is distributed. The surface provides indirect clues. Venus is covered in vast volcanic plains, enormous shield volcanoes, and complex tectonic features such as tesserae, regions of intensely deformed terrain. These features suggest a history of significant internal activity, even if it operates differently from Earth's. Yet there is little evidence for ongoing plate motion. Radar observations from orbit show no clear signs of subduction or spreading ridges. Instead, deformation appears localized and irregular. This supports the idea of a planet that releases internal stress episodically rather than continuously. Despite decades of study, Venus remains one of the most challenging planets to understand. Its interior appears similar enough to Earth's to invite comparison, yet different enough to resist easy explanation. The same size, similar materials, and comparable starting conditions somehow produce two worlds with radically different climates, surfaces, and internal behaviors. This contrast is one of the most valuable lessons Venus offers. It demonstrates that small differences in interior dynamics can lead to enormous differences in outcome. A slight change in how heat escapes, how plates move, or how gases cycle can push a planet onto a completely different evolutionary path. Venus shows that habitability is fragile. It is not guaranteed by size or composition alone. It depends on delicate balances between interior heat, surface processes, and atmospheric chemistry. Once those balances are lost, they may be difficult or impossible to recover. In many ways, Venus is not a failed Earth. It is a successful Venus. Its interior has followed a path that makes sense given its conditions, even if the result is hostile by human standards. Understanding that path requires looking past the surface and into the slow, hidden processes beneath. Venus reminds us that planets do not choose their fate. Their interiors quietly guide them there, one slow geological step at a time. Earth feels solid. Ground underfoot suggests permanent stability, reliability. Mountains seem immovable. Continents appear fixed. Oceans rest quietly in their basins. Yet this sense of stillness is misleading. Beneath the surface, Earth is in constant motion, layered, dynamic, and restless in ways that shape everything visible above. Earth is built like an onion, with distinct layers formed early in its history and still interacting today. The outermost layer is the crust, a thin skin that varies in thickness from place to place. Beneath continents, it can be several tens of kilometers thick. Beneath oceans, it is thinner, denser, and younger. Despite being the only layer directly accessible, the crust contains a tiny fraction of Earth's mass. It is a veneer, not a foundation. Below the crust lies the mantle, a vast region extending thousands of kilometers downward. The mantle makes up most of Earth's volume and mass. It is composed primarily of silicate rock rich in elements such as magnesium, iron, silicon, and oxygen. Although often described as solid, the mantle behaves more like a very slow-moving fluid over geological timescales. Given enough time, rock flows. This slow flow is central to Earth's behavior. Heat from deeper layers causes mantle material to become buoyant and rise. As it cools, it becomes denser and sinks. This movement, known as mantle convection, is driven by temperature differences and the planet's internal heat. The motion is incredibly slow by human standards, often measured in centimeters per year, but over millions of years it reshapes the entire planet. Mantle convection drives plate tectonics. Earth's rigid outer shell is broken into tectonic plates that float atop the convecting mantle. These plates move, collide, separate, and slide past one another. New crust forms at spreading centers. Old crust sinks back into the mantle at subduction zones. Continents drift. Oceans open and close. Mountains rise and erode. No other known planet shows this style of global plate tectonics. This process is not just a geological curiosity. It plays a critical role in regulating Earth's climate and chemistry. Carbon dioxide released by volcanoes is eventually removed from the atmosphere through weathering and plate-driven recycling. Nutrients are redistributed. Heat escapes gradually rather than catastrophically. The planet maintains long-term stability through motion. Below the mantle lies the core, which is divided into two distinct regions. The outer core is a deep layer of liquid metal composed mostly of iron with smaller amounts of lighter elements such as nickel, sulfur, and oxygen. Temperatures here reach several thousand degrees, hot enough to keep metal molten despite the immense pressure. This liquid layer is in constant motion, stirred by heat escaping from the inner core and mantle above. Inside the outer core sits the inner core, a solid sphere of iron and nickel roughly the size of the Moon. Despite being hotter than the surface of the Sun, the inner core remains solid because of the enormous pressure at Earth's center. At these pressures, atoms are forced into rigid arrangements, resisting melting even at extreme temperatures. The existence of the inner core was not always known. In the early 20th century, scientists studying seismic waves noticed something strange. Certain vibrations from earthquakes arrived at detectors in unexpected ways. In 1936, the Danish seismologist Inge Lehmann proposed an explanation that initially seemed bold. Earth's core was not entirely liquid. There had to be a solid inner core reflecting seismic waves in distinctive patterns. Her conclusion was correct. This discovery transformed understanding of Earth's deep interior and provided crucial insight into how the planet generates its magnetic field. The magnetic field arises from the geodynamo. As liquid metal circulates within the outer core, it carries electric charges. Moving charges generate magnetic fields. Under the right conditions, this process sustains itself, producing a stable global magnetic field that extends far into space. Earth's magnetic field shields the planet from much of the charged particle radiation streaming outward from the Sun. This protection matters. Without a magnetic field, Earth's atmosphere would be more vulnerable to erosion by the solar wind. Over long timescales, this could strip away lighter gases, alter climate, and make surface conditions less hospitable. The continued motion of Earth's liquid outer core is therefore intimately linked to the planet's long-term habitability. The inner core plays an important role here as well. As Earth slowly cools, the inner core grows. Liquid metal solidifies onto its surface, releasing heat and lighter elements into the outer core. This process helps drive convection, sustaining the geodynamo. The magnetic field is not a static feature. It fluctuates, drifts, and occasionally reverses direction entirely, but it persists because the deep interior remains active. Earth's layered structure also explains its seismic behavior. When earthquakes occur, they send waves through the planet. Some waves travel quickly through solid rock. Others slow down or stop when they encounter liquid layers. By studying these waves, scientists have mapped Earth's interior with remarkable precision. Sharp boundaries mark transitions between crust and mantle and core, liquid and solid. These boundaries are not just compositional, they are thermal and mechanical. At certain depths, pressure forces minerals into new crystal structures. These phase changes alter how waves travel and how material flows. The mantle, for example, contains regions where rock becomes denser without changing composition, simply because atoms rearrange under pressure. These transitions influence convection patterns and heat transport. Earth's interior is therefore not a simple stack of layers. It is a complex system where temperature, pressure, composition, and motion interact. Heat rises, material circulates, boundaries shift over time. The planet cools slowly, but not uniformly. Some regions remain hot and active. Others become rigid and stable. What makes Earth particularly valuable as a reference world is not that it is typical, but that it is well observed. Seismic networks blanket the planet. Satellites measure gravity and magnetic fields continuously. Samples from volcanic eruptions offer direct clues about mantle composition. No other planet provides this level of access. As a result, Earth serves as the baseline against which all other planetary interiors are compared. When scientists describe the core of Mars, they ask how it differs from Earth's. When they model the mantle of Venus, they begin with Earth's physics and adjust parameters. When interpreting gravity data from Jupiter, Earth's layered structure provides a conceptual starting point, even if the details diverge dramatically. Earth is not the blueprint for all planets, but it is the ruler against which differences are measured. Its dynamic interior shows what is possible when heat, size, composition, and time align in a particular way. Continuous tectonics, a long-lived magnetic field, and stable surface conditions are not inevitable outcomes. They are the result of specific interior processes working together over billions of years. Perhaps the most striking aspect of Earth's interior is how quietly it operates. There is no constant rumbling, no obvious sign day to day of the immense motion beneath the surface. Continents drift at the pace of fingernail growth. Mantle rock flows more slowly than glaciers. The core churns invisibly, generating a magnetic field without sound or light. And yet this slow activity sustains oceans, recycles carbon, protects the atmosphere, and reshapes the planet again and again. Earth's interior is not dramatic in the moment. It is powerful in the long view. By understanding how Earth is layered, how heat moves through it, and how those motions shape the surface, scientists gain a framework for interpreting every other world. Earth is not just home. It is the standard against which the inner lives of planets are understood. The moon appears calm and familiar, hanging quietly in the sky, unchanged within a human lifetime. Its face is marked by dark plains and bright highlands, scars from impacts long past. There is no weather to blur its features, no oceans to erase old wounds. At first glance it feels simple, but beneath that still surface lies a story shaped by heat, violence, and a rapid loss of energy that set the moon apart from every planet. The moon is a small world, and that fact explains almost everything about its interior. Like Earth, the moon is differentiated, meaning its materials are arranged in layers rather than mixed together. It has a crust at the surface, a mantle beneath, and a core at the centre. This layered structure formed early, when the moon was hot enough for materials to separate by density. Dense elements sank inward. Lighter materials floated upward. Even a body far smaller than Earth followed the same basic physical rules. The difference is how quickly those processes ran their course. The lunar crust is relatively thick compared to the moon's size, especially on the far side, where it can be tens of kilometers thicker than the near side. Beneath the crust lies a mantle made mostly of silicate rock, similar in composition to Earth's mantle but far smaller in volume. At the center sits a small core composed primarily of iron, with traces of lighter elements such as sulfur. The core exists, but it is modest. Estimates suggest that the Moon's core makes up only a few % of its total mass. It may have once been partially molten, but it cooled rapidly. Today the Moon has no global magnetic field generated by an active dynamo. Whatever internal motion once existed has long since faded. Understanding the Moon's interior would have been nearly impossible without a rare gift. During the Apollo missions, astronauts placed seismic instruments directly onto the lunar surface. These seismometers recorded vibrations from moonquakes, meteorite impacts, and even the deliberate crashes of spacecraft stages. For the first time, scientists could listen to the inside of another world. The data revealed a surprisingly complex interior. Moonquakes occurred at various depths, some linked to tidal stresses caused by Earth's gravity, others associated with cooling and contraction. Seismic waves reflected and refracted through internal layers, allowing scientists to identify boundaries between crust, mantle, and core. The Moon's interior was quieter than Earth's, but not silent. The seismic signals also behaved differently. On Earth, seismic waves fade relatively quickly as they scatter and are absorbed. On the Moon, vibrations could persist for hours. The dry, fractured lunar crust acts like a bell, ringing long after an impact. This behavior revealed how cold and rigid the Moon's outer layers had become. The Moon cooled fast, and it shows. Its small size meant that heat escaped efficiently. With a large surface area relative to its volume, the Moon radiated its internal energy into space far more quickly than Earth ever could. Within a relatively short geological time, much of its interior solidified. Mantle convection slowed, core motion weakened, geological activity declined. Yet the Moon was not always quiet. In its early history, the Moon experienced extensive volcanism. Vast lava flows erupted from the interior and spread across the surface, filling low-lying basins created by impacts. These flows formed the dark regions known as Lunar Maria. Although they look smooth today, they represent a time when the Moon's interior was still warm enough to generate molten rock. Most of this volcanic activity occurred billions of years ago. Radiometric dating of a lunar samples shows that major volcanic episodes peaked relatively early and then tapered off. As internal heat diminished, magma became harder to produce. Eruptions became rarer and eventually ceased altogether. The Moon transitioned from an active world to a largely inert one. This rapid cooling preserved a record. Because the Moon lacks plate tectonics, weather, and erosion, its surface retains evidence of early solar system history that Earth has long since erased. Craters remain visible for billions of years. Lava plains are frozen in place. Tectonic features caused by contraction remain sharp. The Moon even bears subtle signs of its shrinking interior. As it cooled, the Moon contracted slightly. This contraction created small cliffs known as Labat scarps, where the crust buckled as the interior volume decreased. These features are smaller than those seen on Mercury, but they tell the same story. Cooling leads to contraction. Contraction reshapes the surface. To understand why the Moon cooled so quickly, it helps to consider how it formed. The leading explanation for the Moon's origin is the giant impact hypothesis. According to this model, a Mars-sized body collided with the early Earth. The impact ejected vast amounts of material into orbit. Over time, this debris coalesced to form the Moon. This origin story matters for the interior. The Moon formed from material that had already been heated and processed by Earth's early differentiation. As a result, the Moon is depleted in certain volatile elements and enriched in others. Its composition reflects a mixture of Earth's mantle material and the impactor's remnants. This starting condition influenced how much heat the Moon began with and how quickly it lost it. The Moon also lacks significant radioactive heat sources. Compared to Earth, the Moon contains lower concentrations of long-lived radioactive elements such as uranium and thorium. With less internal heating from radioactive decay, the Moon relied more heavily on its initial heat from formation. Once that heat was gone, there was little to replace it. Size amplifies all of these effects. The Moon's diameter is only a fraction of Earth's. Its gravity is weaker. Pressure in its interior is lower. This limits how hot and dense its core can become. It also reduces the likelihood of sustaining a long-lived molten layer capable of driving a magnetic field. Interestingly, there is evidence that the Moon may have had a magnetic field early on. Magnetized lunar rock suggests that, for a time, the Moon generated its own magnetic field. This field may have been powered by a molten core, tidal interactions with Earth, or mechanical stirring during its early evolution. Whatever the mechanism, it did not last. As the interior cooled, the dynamo shut down. The Moon therefore represents an endpoint. It shows what happens when a rocky body loses its internal heat. Geological activity fades, magnetic protection disappears. The surface becomes a static archive. Change slows to a crawl. In this sense, the Moon is a lesson in planetary scale. Earth is active because it is large enough to stay warm. Mars lingered in a middle state, active for a time before cooling. The Moon crossed the threshold quickly, becoming geologically quiet early in its history. This makes the Moon invaluable for comparison. By studying its interior and evolution, scientists gain insight into how size governs destiny. The same physical laws apply to all rocky bodies, but their outcomes depend strongly on scale. A slight difference in radius can mean the difference between a living planet and a frozen world. The Moon is not dead. It still experiences quakes. Its interior still cools slowly, but it has passed the point where internal heat drives dramatic change. What remains is a world shaped by its early warmth and preserved by its long silence. The Moon shows that planetary interiors do not just shape surfaces, they also determine how long change lasts. Mars has always invited imagination, a reddish world hanging just beyond Earth, close enough to visit, distant enough to feel mysterious. Its surface shows dry river valleys, vast volcanoes, layered sediments, and polar ice. All signs that, long ago, Mars was warmer, wetter, and more dynamic than it is today. The question is not whether Mars changed, but why. The answer lies deep inside. Mars is smaller than Earth, but not dramatically so. It sits in an in-between category, larger than the Moon, much smaller than Earth, and right on the boundary where planetary interiors either stay active for billions of years or slowly fall silent. That boundary shaped Mars's entire fate. At its centre, Mars has a core made primarily of iron, like the other rocky planets. But this core is different in important ways. Data indicate that it contains a relatively high proportion of lighter elements such as sulfur mixed into the iron. These lighter elements reduce the core's density and lower its melting temperature. In its early history, this allowed Mars's core to remain molten, even as the planet began to cool. Surrounding the core is a mantle of silicate rock, similar in composition to Earth's mantle but smaller and thinner. Above that sits a crust that varies significantly in thickness, thicker in the southern highlands and thinner in the northern lowlands. This uneven structure hints at internal processes that once redistributed heat and material before slowing down. For a long time, much of this was inferred indirectly. Gravity measurements, surface composition, and magnetic signatures provided clues, but there was no direct way to listen to the Martian interior. That changed when NASA's InSight mission arrived. InSight placed a highly sensitive seismometer on the Martian surface, designed to detect vibrations traveling through the planet. For the first time, Mars could be heard from the inside. InSight recorded Marsquakes caused by tectonic stresses, cooling, and meteorite impacts. By analyzing how seismic waves traveled through the planet, scientists were able to estimate the size and composition of Mars's core with unprecedented confidence. The results were surprising. The core appeared larger and less dense than many models had predicted, reinforcing the idea that it contained significant amounts of lighter elements. This finding had profound implications. A larger, lighter core would have been fully molten early on, capable of driving a magnetic dynamo. And indeed, Mars shows clear evidence that it once had a global magnetic field. Ancient rocks in the southern highlands are magnetized, preserving a record of a field that existed billions of years ago. But that field did not last. As Mars cooled, its internal heat declined. The smaller size of the planet meant that heat escaped more efficiently than on Earth. Over time, convection within the core slowed. Eventually, the motion required to sustain the dynamo weakened and stopped. When that happened, the global magnetic field collapsed. This was the moment Mars lost its heartbeat. Without a magnetic field, Mars was exposed. Charged particles from the Sun could interact directly with the upper atmosphere. Over long periods, this interaction stripped away lighter gases, particularly hydrogen. Water molecules in the upper atmosphere were broken apart by sunlight, and hydrogen escaped into space. Oxygen reacted with surface materials or was lost more slowly. The atmosphere thinned. As atmospheric pressure dropped, liquid water became unstable on the surface. Rivers dried up. Lakes vanished. Any remaining surface water froze or sublimated. Mars transitioned from a planet that could support flowing water to one dominated by cold, dry conditions. This transformation was not instantaneous. Mars likely spent hundreds of millions of years in a transitional state, with episodic volcanism, intermittent water flow, and a gradually declining atmosphere. Its enormous volcanoes, such as Olympus Mons, testify to a time when the interior was still capable of producing vast quantities of magma. These volcanoes grew so large in part because Mars lacks plate tectonics. Lava erupted repeatedly from the same locations, building towering structures over immense timescales. Eventually, even this activity waned. As the mantle cooled, magma became harder to generate. Volcanic eruptions became less frequent and then ceased altogether. The surface froze into its present form, preserving features from an earlier era like a geological snapshot. Mars occupies a unique position among the rocky worlds. It is not as geologically active as Earth, nor as inert as the Moon. It retained internal heat long enough to develop complex surface features and possibly habitable conditions, but not long enough to sustain them indefinitely. Its interior evolution sits between persistence and loss. This makes Mars invaluable for understanding planetary thresholds. A modest difference in size and composition led to a vastly different outcome. Earth maintained mantle convection, plate tectonics, and a magnetic field for billions of years. Mars did not. The laws of physics did not change between the two planets. Only scale, heat retention, and timing differed. Mars also illustrates how interior processes cascade outward. Cooling of the core led to magnetic field loss. Magnetic field loss led to atmospheric erosion. Atmospheric erosion led to climate collapse. Climate collapse reshaped the surface. Each step followed logically from the one before, all originating deep inside the planet. Today, Mars is quiet but not entirely silent. Marsquakes still occur. The interior continues to cool, albeit slowly. Heat still leaks outward, though insufficient to drive global renewal. The planet has not stopped evolving, but it has entered a late subdued phase of its life. In this sense, Mars is a world caught mid-story. It shows what happens when a planet almost makes it, almost large enough, almost warm enough, almost protected enough. The line between an active world and a frozen one can be narrow, and Mars sits just on the far side of it. By studying Mars's interior, scientists gain insight into the fragile balance that allows planets to remain alive, at least geologically. Mars reminds us that planetary habitability is not guaranteed by early promise. It must be sustained by deep, persistent motion below the surface. When that motion fades, the consequences ripple outward, quietly but relentlessly, until the planet weathers into something very different from what it once was. Most planets hide their interiors behind thousands of kilometers of rock, metal, or gas. Their deepest layers are unreachable, inferred only through indirect signals and careful modelling. Asteroids are different. Some of them do not hide their interiors at all. They display them openly, scattered through space as fragments, offering rare, physical glimpses into the inside of worlds that never quite became planets. Asteroids are often imagined as primitive rubble, leftover debris that never changed. That picture is only partly true. Many asteroids are indeed undifferentiated, meaning their material never separated into layers. They remained mixtures of rock, metal and ice, much as they formed in the early solar system. But a significant number of asteroids tell a far more complex story. They once grew large enough and hot enough for their interiors to melt and reorganize. These are differentiated asteroids. In these bodies, the same basic process occurred as in planets. Heat caused material to soften or melt. Dense metals sank toward the center. Lighter silicate rocks rose upward. A core formed. A mantle developed. In some cases, even a crust emerged. The only difference was scale. Differentiated asteroids were small worlds, but they followed planetary rules. What makes them especially valuable is what happened next. Many of these bodies did not survive intact. Collisions shattered them. Tidal interactions tore them apart. Over time, their layered interiors were exposed, fragmented, and scattered across space. Pieces of cores, mantles, and crusts were separated and sent drifting on their own. Some of those fragments eventually reached Earth. Meteorites are not random rocks. They are samples of specific parts of early planetary bodies. Iron meteorites, for example, are composed almost entirely of metallic iron and nickel. Their crystalline structures show that they cooled slowly, deep inside a parent body large enough to retain heat for long periods. These meteorites are widely interpreted as fragments of exposed asteroid cores. Holding an iron meteorite is like holding a piece of a planetary heart. Stony meteorites tell a different story. Some represent mantle material, rich in silicate minerals. Others preserve crustal components that once sat near the surface of differentiated bodies. Together, these meteorites provide direct, physical evidence that even relatively small objects underwent internal melting and differentiation very early in solar system history. This early melting was driven by heat sources that no longer exist today. Short-lived radioactive isotopes, especially aluminium-26, released large amounts of energy during the first few million years after the solar system formed. Even bodies only tens of kilometers across could heat up enough to partially or fully melt. Timing was critical. Objects that formed early captured this heat and differentiated. Those that formed later missed the window and remained cold and primitive. Meteorites preserve this timing. By measuring isotopic ratios in meteorite samples, scientists can reconstruct when different bodies formed, melted, and cooled. These measurements act like clocks frozen in stone. They show that some asteroids differentiated within the first few million years of solar system history, long before Earth finished forming. This has profound implications. It means that the processes shaping planetary interiors began almost immediately. Differentiation was not reserved for large planets. It was a widespread phenomenon wherever conditions allowed. The solar system was filled with small, short-lived worlds that briefly developed cores, mantles, and internal heat before being destroyed. Asteroids also reveal how diverse planetary interiors can be. Some differentiated bodies developed metal-rich cores. Others were dominated by rock. Some incorporated significant amounts of sulfur or other light elements, altering how their cores behaved. The variety seen in meteorites reflects the variety of conditions present in the early protoplanetary disk. Asteroids are therefore not just leftovers, they are records. They record chemical gradients in the early solar system. They record the intensity and timing of radioactive heating. They record the outcomes of collisions and breakups. Each fragment carries information about an interior that once existed as part of a larger whole. This makes asteroids a bridge between planets and giant worlds. The same physics that governs differentiation in asteroids governs differentiation in Earth, Mars, and Mercury. Scale changes the outcome, but not the underlying rules. By studying small bodies, scientists test models under simpler conditions, where cooling happens faster and structures freeze in place more quickly. Asteroids also help constrain models of giant planet formation. The cores of gas giants are thought to form through the accumulation of solid material early in the solar system. Understanding how metal and rock separate in smaller bodies informs how cores might assemble in much larger ones. The physics scales up, even if the environments differ dramatically. There is a quiet irony here. The smallest bodies, often dismissed as debris, provide the most tangible samples of planetary interiors. While planets keep their secrets buried, asteroids scatter theirs across space, occasionally delivering them directly to Earth's surface. Meteorites have been studied for centuries, but their true significance emerged gradually. Early observers noted their metallic nature and unusual composition. Over time, laboratory analysis revealed cooling rates, crystal structures, and chemical signatures that could only form deep, inside differentiated bodies. What once seemed like odd rocks became key evidence for how planets form and evolve. Asteroids also show that interior evolution can be brief. Some bodies differentiated, cooled, and solidified entirely within a few million years. Their internal activity was intense but short-lived. Others never melted at all. This range of outcomes demonstrates how sensitive planetary interiors are to timing, size, and composition. In that sense, asteroids represent snapshots of early planetary possibilities. Some show what happens when internal heat is abundant but fleeting. Others show what happens when it never arrives. Together they outline the boundaries within which planets must operate. They also provide context. Without asteroids and meteorites, understanding of planetary interiors would rely entirely on indirect methods. With them, scientists can test models against real samples. Predictions about core composition, cooling rates, and differentiation can be checked against physical evidence. Asteroids remind us that not all worlds mature. Many begin the journey toward becoming planets and fail along the way. but in failing they preserve records that would otherwise be erased by ongoing geological activity. Their broken interiors become archives rather than engines of change. As attention turns outward, toward gas giants and ice giants, asteroids serve as a quiet foundation. They show that the story of planetary interiors begins small, fast, and early. Before massive worlds took shape, countless minor ones briefly burned with internal heat, sorted their materials, and then vanished. What remains of them drifts between planets, carrying pieces of planetary interiors in plain sight, waiting to be found. Jupiter does not have a surface in the way rocky planets do. There is no solid ground to stand on, no clear boundary where sky becomes land. Instead, Jupiter is a gradual descent, layer after layer, each one stranger and more extreme than the last. To imagine its interior is to let go of everyday intuition and accept a world shaped almost entirely by pressure. From the outside, Jupiter appears familiar enough. Bands of clouds circle the planet, storms churn and drift. The Great Red Spot has raged for centuries, yet all of this visible motion is only a thin skin atop a vast interior that holds most of the planet's mass and energy. Jupiter is enormous. It contains more than twice the mass of all the other planets combined. This immense gravity compresses everything beneath the clouds, creating pressures so extreme that matter behaves in unfamiliar ways. The deeper one goes, the less useful everyday categories like gas, liquid, and solid become. The outermost layers of Jupiter are dominated by hydrogen and helium, the lightest elements in the universe. Near the top, hydrogen behaves as a gas, forming clouds mixed with trace compounds such as ammonia and water. As pressure increases with depth, the gas becomes denser. Molecules crowd closer together. The distinction between gas and liquid begins to blur. Eventually, hydrogen enters a state that has no true counterpart on Earth. Under pressures millions of times greater than Earth's atmosphere, hydrogen is squeezed so tightly that its electrons move freely. The hydrogen becomes electrically conductive. This exotic phase is known as metallic hydrogen, and it likely makes up a large fraction of Jupiter's interior. Metallic hydrogen is not a metaphor. It behaves like a metal. It conducts electricity. It responds to magnetic fields, and under Jupiter's conditions it may exist as a fluid, flowing slowly beneath the planet's outer layers. This vast region of metallic hydrogen is central to Jupiter's behavior. As metallic hydrogen moves, it generates electric currents. Those currents produce a powerful magnetic field through a dynamo process similar in principle to Earth's, but vastly larger in scale. Jupiter's magnetic field is the strongest of any planet in the solar system. It extends millions of kilometers into space and traps enormous amounts of charged particles. The source of that field lies deep inside. Below the metallic hydrogen region, Jupiter may contain a core enriched in heavier elements. For decades, scientists debated the nature of this core. Early models imagined a compact solid core made of rock and ice, roughly 10 times the mass of Earth. This idea fit neatly with core accretion models of giant planet formation, where a solid core forms first and then captures gas from the surrounding disk. But Jupiter resisted simplicity. Data from NASA's Juno mission transformed understanding of the planet's interior. Juno measures Jupiter's gravitational field with extraordinary precision by tracking tiny changes in the spacecraft's motion as it orbits close to the planet. These measurements revealed that Jupiter's mass is not distributed as cleanly as expected. Instead of a sharply defined core, the data suggest a more diffuse region, where heavy elements are spread out over a large volume. Rather than a neat boundary between core and envelope, Jupiter appears to have a fuzzy or diluted core blending gradually into the surrounding metallic hydrogen. This was unexpected. It implies that Jupiter's early history involved intense mixing, perhaps driven by enormous impacts or vigorous convection during formation. Heavy elements may have been stirred outward, smearing the core across a significant fraction of the planet's radius. Jupiter's interior may be less layered and more blended than once thought. Despite this complexity, Jupiter is far from quiet inside. The planet emits more energy than it receives from the Sun. This excess heat comes from two main sources. One is residual heat left over from formation. Jupiter formed quickly and captured a vast amount of gravitational energy, much of which remains trapped inside. The other source is ongoing gravitational contraction. As Jupiter slowly compresses under its own gravity, it releases heat. This process, known as Kelvin-Helmholtz contraction, continues even today. The planet shrinks by a tiny amount over time, converting gravitational energy into thermal energy. This internal heat powers Jupiter's atmosphere. Warm material rises, cooler material sinks. Convection drives the banded cloud structure, fuels storms, and sustains features like the Great Red Spot. The atmosphere is not merely responding to sunlight, it is being energized from below. Jupiter's weather is therefore deeply connected to its interior. Storms can reach thousands of kilometers in size because they draw energy from a vast internal reservoir. Winds blow at incredible speeds. Patterns persist for decades or centuries because the planet's heat engine operates continuously. The interior also influences how Jupiter rotates. The planet does not rotate as a rigid body. Different latitudes rotate at different rates, and this differential rotation may extend deep into the interior. Juno's gravity measurements suggest that atmospheric jet streams penetrate thousands of kilometers below the visible clouds, coupling surface motion to deeper layers. This connection blurs the line between atmosphere and interior. On Jupiter, weather is not just surface decoration. It is a manifestation of deep internal dynamics, reaching down into regions of extreme pressure and density. Despite the advances made by Juno, significant uncertainties remain. The exact composition of Jupiter's core region is still debated. How much rock and ice does it contain? How sharply does composition change with depth? How efficiently does heat move through metallic hydrogen? These questions are difficult to answer because they depend on material behavior under conditions that are challenging to reproduce even in the most advanced laboratories. Metallic hydrogen itself remains an active area of research. While it has been produced briefly under laboratory conditions, Jupiter's version exists at pressures and temperatures that push theoretical models to their limits. Small changes in assumptions about conductivity, viscosity, or phase transitions can lead to different interior structures. This uncertainty is not a failure of science, it is a reflection of scale. Jupiter is a natural experiment far larger than anything humans can build. Its interior tests physics in regimes unreachable on Earth. Each new measurement refines understanding, but the full picture emerges slowly. Jupiter also serves as a reference point. By understanding Jupiter's interior, scientists gain insight into giant planets throughout the galaxy. Many of the most common exoplanets discovered are Jupiter-sized or larger. Interpreting their masses, radii, and atmospheric properties depends on knowing how matter behaves under the conditions found inside Jupiter. In this sense, Jupiter is both a planet and a laboratory. Its interior connects planetary science to condensed matter physics, fluid dynamics, and magnetohydrodynamics. It demonstrates how gravity alone can create environments so extreme that familiar elements adopt entirely new identities. Perhaps the most striking aspect of Jupiter's interior is how invisible it is. Nothing at the surface hints directly at metallic hydrogen or diffuse cores. The clouds offer no signposts, and yet beneath them lies a world defined by pressure beyond imagination, where hydrogen conducts electricity, heat flows relentlessly upward, and gravity dominates every interaction. Jupiter reminds us that size changes everything. The same elements found in Earth's oceans and rocks become something entirely different when subjected to enough mass and compression. The interior of Jupiter is not just larger than Earth's. It is governed by different physical regimes altogether. To understand Jupiter is to accept that planets are not scaled versions of one another. They are shaped by thresholds, cross a certain mass, and new physics takes over. Jupiter crossed that threshold early, and its interior has been rewriting the rules ever since. Saturn looks delicate from afar. Pale bands wrap gently around its globe, the rings spread outward like something drawn rather than built, thin and luminous, almost weightless. Yet this softness is an illusion. Saturn is a giant world, massive and deep, and its interior is shaped by forces as extreme as those inside Jupiter, even if they express themselves more quietly. One of Saturn's most famous facts is also one of its most misleading. It is often said that Saturn is so low in density that it could float in water. While this is technically true in a purely numerical sense, it hides the real story. Saturn is not light because it lacks mass. It is light because its mass is spread out over a very large volume. Like Jupiter, Saturn is made mostly of hydrogen and helium. Unlike Jupiter, it is less compressed. This difference matters. Saturn's lower density tells scientists that its interior pressure is lower than Jupiter's at equivalent depths. The same ingredients are present, but they are arranged under gentler compression. As a result, Saturn's interior crosses physical thresholds at different depths, creating a structure that is similar in outline but distinct in detail. The outer layers of Saturn are dominated by hydrogen and helium gas, mixed with trace compounds that form clouds. As depth increases, pressure rises and hydrogen becomes denser, transitioning gradually toward a liquid-like state. Deeper still, hydrogen begins to take on metallic properties, conducting electricity as its electrons move freely. But here Saturn diverges. Inside Saturn, the conditions that create metallic hydrogen overlap with another important process involving helium. Under the immense pressures and temperatures inside the planet, helium does not always remain evenly mixed with hydrogen. Instead, it can separate. This process is known as phase separation. At certain depths, helium becomes less soluble in hydrogen. It begins to clump together, forming droplets that fall downward under gravity. This phenomenon is often called helium rain, though it bears little resemblance to rain as experienced on Earth. These droplets descend through the interior, releasing gravitational energy as heat. Helium rain helps explain one of Saturn's long-standing mysteries. Saturn emits more energy than it receives from the Sun. This excess heat cannot be explained by residual heat from formation alone. Over time, Saturn should have cooled more than it has. The ongoing separation and sinking of helium provides an additional energy source, releasing heat deep inside the planet and slowing its cooling. In effect, Saturn is warmed from within by falling helium. This internal rain does not reach the surface. It occurs far below the visible clouds, in regions where pressure and temperature force hydrogen and helium into unfamiliar states. The heat released by this process rises slowly, contributing to Saturn's internal energy budget and influencing its atmospheric behavior. The planet's layered structure reflects these processes. Above the region of helium rain lies a hydrogen-rich envelope. Below it may be a deeper layer enriched in helium. Deeper still, Saturn likely contains a region where heavier elements are mixed with metallic hydrogen, forming a diffuse core rather than a sharply defined one. Like Jupiter, Saturn does not appear to have a neat boundary between core and envelope. Gravity measurements from the Cassini mission provided key insight here. By tracking how Saturn's gravity affected the spacecraft's trajectory during close flybys, scientists mapped the distribution of mass inside the planet. The data suggest that Saturn's interior contains a broad region enriched in heavy elements, rather than a compact, isolated core. This resemblance to Jupiter hints at a shared history. Both planets likely formed through rapid accretion of solid material followed by the capture of large amounts of gas. In both cases, early mixing, impacts, and vigorous convection may have blurred the boundaries between layers. The difference is that Saturn, being smaller and cooler, expresses these processes differently. Saturn's magnetic field reflects this. Like Jupiter, Saturn has a strong magnetic field generated by motion in its electrically conductive interior. However, Saturn's magnetic field is unusually symmetric, aligned very closely with its rotation axis. This near-perfect alignment puzzled scientists for decades, because dynamo theory typically predicts some degree of tilt or asymmetry. One possible explanation lies in Saturn's internal layering. If the region generating the magnetic field is surrounded by a stable, stratified layer created by helium rain, this could suppress certain types of motion and produce a more orderly magnetic field. In this view, Saturn's interior structure acts as a filter, shaping how the dynamo operates. This is still an area of active research. Saturn's atmosphere, like Jupiter's, is powered in part by internal heat. Winds, storms, and banded cloud patterns draw energy from below as well as from sunlight. However, Saturn's atmospheric features are generally more subdued. Storms occur, but they are less intense and less persistent than Jupiter's most famous systems. Again, scale and heat make the difference. Saturn has less mass, lower pressure, and a smaller internal energy reservoir than Jupiter. Its weather reflects this gentler engine. The planet still convects, still churns, still releases heat, but it does so with less violence. Despite its calm appearance, Saturn's interior is far from static. Helium continues to separate, heat continues to rise, the planet continues to cool, though slowly. Over time, the balance between hydrogen and helium will shift further. The interior will evolve, the magnetic field may change, the atmosphere may respond. Saturn therefore represents a later stage of giant planet evolution. Compared to Jupiter, it is cooler, less compressed, and more influenced by ongoing phase separation. Compared to ice giants like Uranus and Neptune, it is still massive enough to retain large amounts of hydrogen and helium and to generate a strong magnetic field. This makes Saturn a bridge. It links the extreme pressure-dominated interior of Jupiter with the more compositionally complex interiors of the ice giants. By comparing Saturn to Jupiter, scientists isolate the effects of mass and pressure. By comparing Saturn to Uranus and Neptune, they isolate the effects of composition and heat transport. Saturn's rings, while not part of its interior, offer a poetic contrast. Above the planet, ice and rock orbit in delicate balance, tracing gravity in thin, shimmering arcs. Below the clouds, helium sinks through hydrogen, releasing heat that has been trapped since the planet's birth. Above, motion is graceful and visible. Below, it is slow, hidden, and relentless. Both are governed by the same physics. Gravity pulls inward, energy seeks lower states, structures evolve over time, The difference is only where the processes unfold. Saturn reminds us that not all giant planets are interchangeable. Even when made of similar materials, differences in mass, temperature, and pressure lead to different internal behaviors. Helium rain may be insignificant in Jupiter and impossible in smaller planets, but in Saturn it becomes a defining feature. In this way, Saturn teaches a subtle lesson. Planetary interiors are not just determined by what they're made of, but by where they sit relative to critical thresholds. Cross one boundary and a new process turns on. Fall below another and a process fades away. Saturn sits in a narrow window where helium rain matters, where internal heat lingers, and where gravity is strong enough to shape a giant, but not strong enough to erase every distinction. Beneath the rings and clouds, Saturn is quietly sorting itself, one droplet at a time. Uranus is the planet that refuses to sit upright. While the other worlds spin more or less straight, Uranus rolls through space on its side, its axis tilted so dramatically that its poles take turns pointing almost directly at the Sun. This single fact dominates how Uranus looks, how it behaves, and likely how its interior evolved. But the tilt is only the most visible clue. Beneath the clouds, Uranus hides an interior that is as unusual as its orientation. Uranus belongs to a category known as the ice giants. Unlike Jupiter and Saturn, which are dominated by hydrogen and helium, Uranus contains a much higher proportion of heavier compounds. Its interior is thought to consist of three broad regions. At the centre lies a rocky core made of silicate material and metals. Surrounding that core is a thick mantle rich in what planetary scientists call ice, though this term is misleading. Above that mantle sits a relatively thin envelope of hydrogen and helium. The ice-rich mantle is the defining feature. In planetary science, ice does not mean frozen water alone. It refers to volatile compounds such as water, ammonia, and methane that were able to condense in the colder outer regions of the early solar system. Inside Uranus, these substances are not frozen in the familiar sense. They exist under enormous pressure and temperature, forming dense exotic fluids. This mantle may make up the majority of Uranus's mass. Water, ammonia, and methane are squeezed into states that behave neither like ordinary liquids nor solids. Electrical conductivity may arise. Chemical bonds may rearrange. These materials likely play a key role in how Uranus generates its magnetic field, which is strangely oriented and offset from the planet's centre. At the very centre, Uranus probably has a compact rocky core. Estimates suggest it is only a few times the mass of Earth, small compared to the planet's overall size. The core is likely hot, but whether it is partially molten remains uncertain. The limited data available leave room for multiple interpretations. Uranus's most famous feature, its extreme axial tilt, adds another layer of mystery. The planet is tilted by roughly 98 degrees, meaning it effectively spins on its side. During parts of its long year, one hemisphere faces the Sun continuously, while the other remains in darkness. This unusual orientation almost certainly resulted from a violent event early in the planet's history, most likely a massive collision with another large body. Such an impact would not only tip the planet, it could also disrupt the interior. A collision of that scale would inject enormous energy, potentially altering internal layering, redistributing heat, and changing how materials mix. Some models suggest that Uranus's interior may have been reorganized by such an event, leaving behind long-lasting consequences. One of those consequences may be Uranus's strangest trait. Despite being similar in size to Neptune, Uranus emits very little internal heat. Measurements show that Uranus radiates roughly the same amount of energy it receives from the Sun, indicating that its internal heat source is weak. This is in stark contrast to Neptune, which emits significantly more energy than it absorbs. Why Uranus is so cold inside remains one of the great puzzles of planetary science. One possibility is that Uranus lost much of its internal heat early, perhaps as a result of the same collision that tilted it. If heat was transported outward efficiently after the impact, the planet may have cooled rapidly. Another possibility involves how heat moves through the interior today. This leads to the idea of layered convection. In a simple model, heat rises from the core through the mantle and escapes at the surface. But if the interior is compositionally stratified, with layers of different materials stacked atop one another, convection can be suppressed. Hot material may become trapped beneath stable layers, unable to rise efficiently. If Uranus's ice-rich mantle is strongly layered, heat could be locked deep inside. This would explain why the planet appears cold on the outside despite potentially retaining warmth within. Heat may still be present, but it is not reaching the surface in large amounts. The planet becomes insulated by its own internal structure. Layered convection would also affect the magnetic field. Uranus has a magnetic field that is tilted and offset, unlike the relatively symmetric fields of Earth, Jupiter and Saturn. The field appears to originate not from the deep core, but from a region closer to the mantle. This supports the idea that electrically conductive fluids in the ice mantle, rather than metallic cores alone, are responsible for the dynamo. The result is a magnetic field that wobbles and twists as the planet rotates. Charged particles follow complex paths. The magnetosphere behaves in ways not seen elsewhere in the solar system. Once again, Uranus defies simple expectations. The lack of internal heat also shapes Uranus's atmosphere. Compared to Neptune, Uranus appears relatively bland. Its winds are slower. Storms are less frequent. Atmospheric activity is muted. Without a strong internal heat source driving convection, the atmosphere relies more heavily on sunlight for energy. Even here, the tilt plays a role. Seasonal extremes caused by Uranus's orientation may drive atmospheric changes on long timescales, but these effects are slow and subtle. The planet's atmosphere responds gently, reflecting the quiet engine below. Despite decades of study, Uranus remains poorly understood. Only one spacecraft, Voyager 2, has flown past it, providing a brief snapshot rather than sustained observation. Much of what is known about Uranus's interior comes from indirect measurements and modelling. Gravity data suggest mass distribution, but cannot uniquely determine internal layering. Magnetic field data hint at conductive regions, but leave room for interpretation. Key questions remain open. How exactly is heat distributed inside Uranus? How strong is compositional layering? Did a giant impact permanently alter the interior, or are current conditions the result of slow evolution? Is there still significant heat trapped deep inside waiting to escape? These uncertainties make Uranus scientifically valuable. It represents an alternative outcome for a planet of its size. Where Neptune retained heat and activity, Uranus became subdued. Where Jupiter and Saturn show powerful internal engines, Uranus whispers. This contrast highlights how sensitive planetary interiors are to early events. A collision at the wrong time, a slight difference in composition, a change in how materials separate. Any of these can redirect a planet's entire evolutionary path. Uranus shows that not all ice giants are alike. It occupies a unique corner of planetary possibility, where extreme tilt, suppressed heat flow, and unusual magnetic behavior coexist. Its interior may be layered, disrupted, or quietly insulated, but whatever the case, it challenges assumptions built from studying other worlds. In the end, Uranus is a reminder that planets do not always reveal their secrets willingly. Some hide them beneath calm exteriors and awkward orientations, offering only hints through subtle measurements. Understanding Uranus requires patience, careful modelling, and the acceptance that some answers remain provisional. The planet rolls onward through space, tilted and quiet, carrying an interior shaped by violence, chemistry and time, still waiting to be fully understood. Neptune is distant, dark, and deceptively energetic. From its place at the edge of the solar system, it receives only a small fraction of the sunlight that reaches Earth. Its clouds are cold, its light is faint, and yet Neptune radiates far more energy than it absorbs from the sun. Something deep inside is generating heat, and it does so with surprising intensity. This makes Neptune an outlier. Like Uranus, Neptune is classified as an ice giant. Its overall size and mass are similar. Its composition follows the same broad pattern. A rocky core sits at the centre. Above it lies a thick mantle rich in water, ammonia and methane. Surrounding that mantle is a relatively thin outer envelope of hydrogen and helium. From the outside, Neptune and Uranus look like siblings. Inside, they behave very differently. Neptune's interior appears to be more active. Measurements show that Neptune emits more than twice as much energy as it receives from the Sun. This excess heat powers vigorous convection, driving some of the fastest winds observed on any planet. Storm systems race through its atmosphere. Dark vortices appear and disappear. The planet looks alive in motion, despite its great distance from the Sun. The source of this energy lies below the clouds. Neptune's ice-rich mantle is thought to be warm and dynamic. Under immense pressure, water, ammonia and methane form dense fluids that can flow and convect. Heat rises from deeper layers and is transported outward, reaching the atmosphere and shaping weather patterns. This process seems far more efficient on Neptune than on Uranus. Where Uranus appears insulated, Neptune appears open. Heat escapes readily. The interior remains active. The difference between the two planets is striking because their sizes and compositions are so similar. This contrast makes Neptune one of the most important test cases for understanding how planetary interiors work. Several explanations have been proposed. One possibility is that Neptune simply retained more heat from its formation. If it formed slightly later or under different conditions, it may have trapped more internal energy. Another possibility involves differences in internal structure. Neptune's mantle may be less compositionally layered, allowing convection to operate more freely. Layered convection again plays a role. If Uranus has strong compositional stratification that suppresses heat flow, Neptune may lack such stable layers. Without barriers to motion, hot material can rise more easily, carrying energy upward. This would naturally produce a higher heat output. Impacts may also matter. Just as a giant collision may have disrupted Uranus's interior and altered its heat flow, Neptune may have avoided such a fate, or experienced impacts that enhanced mixing rather than suppressing it. Small differences in early history can have large consequences billions of years later. Neptune's magnetic field adds another clue. Like Uranus, Neptune has a magnetic field that is tilted and offset from the planet's center. This suggests that the field is generated not in a deep metallic core, but in electrically conductive fluids within the ice-rich mantle. The Dynamo region may be relatively shallow compared to gas giants. Despite this similarity, Neptune's magnetic activity appears more vigorous. A warmer, more mobile mantle would support stronger electrical currents and more dynamic magnetic behavior. This again points to an interior where heat and motion are not trapped, but actively circulating. The connection between interior heat and atmosphere is especially clear on Neptune. The planet's winds can exceed 2,000 kilometers per hour, faster than those on Jupiter or Saturn. These winds are not driven primarily by sunlight. At Neptune's distance, solar energy is weak. Instead, internal heat provides much of the energy that powers atmospheric motion. Warm material rising from below creates temperature contrasts that drive convection and circulation. Storms form, migrate, and dissipate. The atmosphere responds directly to the planet's internal engine. This makes Neptune a reminder that distance from the Sun is not the only determinant of activity. A planet can be cold at the surface and still internally energetic. It can be far from its star and yet dynamic. Internal heat can compensate for weak external input. Neptune's interior likely continues to evolve. As the planet slowly cools, heat loss will eventually decrease. Convection may weaken, atmospheric activity may subside, but this process unfolds over immense timescales, measured in billions of years. For now, Neptune remains active, its interior still releasing energy captured long ago. Despite this, many details remain uncertain. The exact distribution of materials inside Neptune is not well constrained. Gravity data provide hints, but cannot uniquely determine layering. Laboratory experiments on water and ammonia at extreme pressures inform models, but uncertainties remain. The precise mechanism that allows Neptune to shed heat so efficiently is still debated. This uncertainty is scientifically valuable. Neptune sits at the boundary between different interior regimes. It is massive enough to retain heat and drive convection, but not so massive that hydrogen dominates its behavior entirely. It occupies a middle ground where composition, structure, and heat flow interact in subtle ways. By comparing Neptune with Uranus, scientists isolate the effects of internal structure. By comparing Neptune with Jupiter and Saturn, they isolate the effects of composition. Neptune helps complete the picture of how planetary interiors operate across a wide range of masses and environments. There is also a broader implication. Many exoplanets discovered in recent years fall into a size range similar to Uranus and Neptune. Understanding Neptune's interior helps interpret observations of these distant worlds. When astronomers measure an exoplanet's radius and mass, they rely on models grounded in planets like Neptune to infer composition and structure. Neptune therefore extends its influence far beyond the solar system. It anchors theories about ice giants everywhere. Its unexplained heat challenges assumptions and forces refinements. Each unanswered question sharpens understanding rather than diminishing it. Perhaps the most intriguing aspect of Neptune is that it should not be as active as it is. Given its distance, its age, and its size, simple models predict a quieter interior. And yet, the planet contradicts those expectations. Heat rises, winds roar, storms form. Neptune is a lesson in humility. It shows that planetary interiors cannot always be reduced to simple rules. Similar starting points can diverge. Small differences can amplify. Outcomes can surprise. In Neptune, heat persists where it should have faded. Motion continues where it might have stalled. The planet keeps revealing that even at the edge of the solar system, deep interiors can remain restless, long after sunlight has lost its strength. Neptune does not offer a final explanation. It offers a challenge. When planetary scientists talk about ice inside giant planets, they're not talking about anything that could be chipped, melted, or slipped on. The word ice survives out of historical habit, not because it accurately describes what exists deep inside these worlds. Inside giant planets, ice becomes something else entirely, reshaped by pressures and temperatures so extreme that familiar categories stop working. In everyday experience, ice is simple. Water freezes, molecules lock into a crystalline lattice, heat melts it, pressure cracks it. That intuition collapses almost immediately when conditions depart from Earth's surface. Inside giant planets, pressure rises faster than temperature intuition can keep up with, and water becomes one of the strangest substances in the solar system. In the interiors of Uranus and Neptune, water, ammonia, and methane dominate large regions of the mantle. These compounds are called ices because they condensed as solids in the cold outer regions of the early solar system. That origin defines the name, not their present state. Today, deep inside these planets, none of these substances behave like frozen solids. Pressure changes chemistry. As depth increases, molecules are forced closer together. Atomic distances shrink. Electrons rearrange. Chemical bonds stretch, break, and reform. Water molecules that behave politely at Earth's surface are crushed into unfamiliar arrangements, creating phases that cannot exist naturally anywhere on Earth. One of the most remarkable of these phases is superionic water. In this state, oxygen atoms form a rigid lattice, locked into place like a solid, while hydrogen ions move freely through the structure like a liquid. The material is neither fully solid nor fully liquid. It is something in between, with properties of both. Superionic water conducts electricity exceptionally well, making it especially important for planetary interiors. This phase was predicted theoretically before it was ever observed. Laboratory experiments using diamond anvil cells and powerful lasers later confirmed that water can enter a superionic state under pressures millions of times greater than Earth's atmosphere and temperatures of several thousand degrees. These are exactly the conditions expected inside ice giants. Ammonia and methane also behave strangely. Under extreme pressure, ammonia may break apart and recombine into ionic fluids. Methane can decompose, releasing hydrogen and forming heavier hydrocarbons or even diamond-like structures. In fact, experiments suggest that carbon atoms from methane may crystallize into diamond and sink deeper into the planet, a process sometimes referred to as diamond rain. This is not poetic exaggeration. Under sufficient pressure, carbon bonds rearrange into diamond lattices. These crystals would be denser than their surroundings and fall inward, releasing gravitational energy as heat. Whether this process occurs extensively inside Uranus or Neptune remains uncertain, but it is physically plausible and supported by laboratory results. Together, these exotic states create an interior environment unlike anything seen on rocky planets. Instead of solid rock and liquid metal, ice giant mantles may consist of hot, dense, electrically conductive fluids composed of water, ammonia, methane, and their breakdown products. These materials can flow, convect, and carry electric currents, all while existing under pressures that defy ordinary language. This has direct consequences for magnetic fields. On Earth and Jupiter, magnetic fields are generated primarily by motion in metallic cores or metallic hydrogen layers. In Uranus and Neptune, the situation is different. Their magnetic fields are tilted, offset, and irregular. This strongly suggests that the Dynamo region is not deep in a central core, but in the surrounding mantle. Superionic and ionic water-rich fluids provide a solution. If large regions of the mantle are electrically conductive, convection within these layers can generate magnetic fields. Because the geometry and motion of these layers differ from those in spherical cores, the resulting magnetic fields are asymmetric and complex. The strange magnetospheres of Uranus and Neptune may therefore be direct expressions of exotic ice physics. Chemistry under pressure also affects heat transport. In rocky mantles, heat moves through slow convection of solid rock. In metallic hydrogen, heat moves through fluid motion and electrical conduction. In ice giant mantles, heat may move through a combination of fluid convection, chemical separation, and phase transitions. Each mechanism responds differently to temperature and composition. This complexity helps explain why Uranus and Neptune behave so differently despite their similarities. If Uranus's mantle is strongly layered, with stable compositional gradients, convection may be suppressed. Heat becomes trapped. The planet cools quietly. If Neptune's mantle is more mixed, convection proceeds efficiently and heat escapes. The difference may hinge on subtle variations in how these exotic materials separate and flow. The term ice, therefore, conceals more than it reveals. It suggests coldness, stillness, and rigidity. In reality, ice giant interiors may be among the most chemically active regions in the solar system. Bonds break, phases shift. Materials conduct electricity and generate magnetic fields. All of this happens in darkness, under crushing pressure, over billions of years. Laboratory experiments continue to push understanding forward. Facilities that recreate extreme pressures allow scientists to probe how water and ammonia behave under planetary conditions. Computational models extend these results, predicting phase diagrams that guide interior models. Each new experiment refines understanding of where transitions occur and how materials behave once they cross them. Yet uncertainty remains unavoidable. The exact composition of ice giant mantles is not known. Small changes in ratios of water, ammonia, and methane can alter conductivity, density, and convection behavior. Temperature profiles are uncertain. Phase boundaries may shift depending on impurities and mixing. Interior models must therefore remain flexible. This uncertainty is not weakness. It reflects the reality that ice giants occupy a regime where multiple physical processes overlap. Chemistry, thermodynamics, and fluid dynamics all interact. No single factor dominates. Understanding emerges only by considering how these processes combine. Ice giants expand the definition of planetary interiors. They show that worlds are not limited to rock and gas. They introduce a third category, where volatile compounds under extreme pressure become the dominant actors. These interiors challenge assumptions built from Earth and Jupiter and demand new physics. They also extend relevance beyond the solar system. Many exoplanets discovered to date fall into the size range of Uranus and Neptune. Interpreting their densities and radii depends critically on understanding exotic ice behavior. Without it, conclusions about composition and structure would be deeply uncertain. In this sense, ice is not a footnote. It is a central theme in planetary diversity. The physics of high-pressure water, ammonia, and methane shapes magnetic fields, heat flow, and long-term evolution for a vast class of planets. What ice means inside giant planets is therefore not coldness, but transformation. It is matter pushed beyond familiarity, adopting new identities under pressure. It is chemistry rewritten by gravity. And it is a reminder that the universe does not limit itself to the states of matter most comfortable to human experience. Inside giant planets, ice becomes something else entirely, and that difference changes everything. A magnetic field is invisible, intangible, and easy to forget. It cannot be seen directly, cannot be touched, and announces itself only through subtle effects. Yet across the solar system, magnetic fields reveal some of the most important truths about what is happening deep inside planets. They are signatures of motion in places no probe can reach. Magnetic fields do not arise by accident. They're generated by a process known as the dynamo mechanism. For a dynamo to operate, three basic conditions must be met. There must be an electrically conductive material. That material must be in motion. And the motion must be sustained over long periods of time. When these conditions are satisfied, moving electric charges create magnetic fields, and those fields reinforce the motion that created them. This process is self-sustaining but delicate. If motion slows, the field weakens. If conductivity drops, currents fade. If heat flow changes, convection patterns shift. Magnetic fields therefore act as sensitive indicators of a planet's internal state. When a planet has a magnetic field, something deep inside is moving. On Earth, the conductive layer is liquid iron in the outer core. Heat escaping from the inner core and mantle drives convection in this molten metal. As the fluid moves, it carries electric charges. Earth's rotation helps organize this motion, producing a coherent global magnetic field. This field is not static. It drifts, fluctuates, and occasionally reverses direction entirely, but it persists because the interior remains active. This same basic principle applies elsewhere, but with variations. On Jupiter and Saturn, the conductive layer is metallic hydrogen rather than molten iron. Under extreme pressure, hydrogen behaves like a liquid metal, allowing electric currents to flow. Convection in this vast region generates powerful magnetic fields, far stronger than Earth's. Jupiter's magnetic field is the most intense of any planet, enveloping a volume of space large enough to swallow the Sun. In Uranus and Neptune, the picture changes again. Their magnetic fields are tilted and offset, suggesting that the dynamo operates in a different region. Instead of a deep central core, electrically conductive fluids in the ice-rich mantle likely generate the field. Superionic water and ionic mixtures of ammonia and methane provide the conductivity. Convection in these layers produces magnetic fields that are complex and irregular. These differences highlight an important point. Magnetic fields do not require a specific material. They require conductivity and motion. Iron works. Metallic hydrogen works. Exotic ionic fluids work. What matters is whether the planet's interior creates the right conditions. Some planets fail to do so. Venus, despite being similar in size and composition to Earth, has no detectable global magnetic field. The most likely explanation is not a lack of iron, but a lack of motion. If Venus's core is largely solid, or if temperature differences are too small to drive convection, the dynamo shuts down. Liquid metal sitting quietly does not generate a magnetic field. Mars tells a related story. Evidence preserved in ancient rock shows that Mars once had a magnetic field. Its core was once molten and convecting. Over time, as the planet cooled, that motion slowed and stopped. The dynamo faded. What remains today are patches of magnetized crust, frozen records of a field that no longer exists. Mercury complicates the picture. Despite its small size, Mercury has a weak but persistent magnetic field. This suggests that part of its core remains molten and convecting. The presence of lighter elements such as sulfur may have lowered the melting temperature, allowing liquid metal to persist longer than expected. Mercury demonstrates that size alone does not determine magnetic fate. The Moon, by contrast, lost its field early. Although there is evidence that the Moon once generated a magnetic field, it cooled quickly. Its small size allowed heat to escape rapidly. Core motion ceased. The dynamo shut down. Today, the Moon has no global magnetic field, only faint remnants locked into ancient rocks. Magnetic fields therefore track internal lifetimes. They appear when interiors are warm and dynamic. They weaken as heat escapes. They vanish when motion stops. In this way, a magnetic field can be thought of as a planet's pulse. When it fades, the interior has entered a quieter phase. Beyond their origin, magnetic fields shape a planet's relationship with space. A magnetic field interacts with the solar wind, deflecting charged particles and carving out a region known as a magnetosphere. This region acts as a shield, reducing the direct impact of high-energy particles on the atmosphere and surface. On Earth, this shielding is critical. The magnetosphere deflects much of the solar wind, preventing it from directly stripping atmospheric gases. It also channels charged particles toward the poles, producing auroras. While not perfect protection, the magnetic field significantly reduces atmospheric erosion over long timescales. Planets without magnetic fields are more exposed. On Mars and Venus, the solar wind interacts directly with the upper atmosphere. Over billions of years, this interaction can remove lighter gases, particularly hydrogen. On Mars, this process contributed to the loss of water and the thinning of the atmosphere. On Venus, it likely played a role in shaping the current dry, dense atmosphere. Gas giants offer a different perspective. Jupiter's immense magnetic field traps vast numbers of charged particles, creating intense radiation belts. These belts pose serious hazards to spacecraft. The same field that shields the planet's atmosphere also creates an environment hostile to electronics and unprotected life. Magnetic protection is not universally gentle. The strength and shape of magnetospheres vary widely. Earth's magnetosphere is moderate in size and relatively stable. Jupiter's is enormous and violent. Saturn's is strong but unusually symmetric. Uranus and Neptune have magnetospheres that wobble dramatically as the planets rotate, exposing different regions to charged particles in complex patterns. These differences reflect interior dynamics, the geometry of the conductive region, the vigor of convection, and the influence of rotation all shape the resulting magnetic field. By studying magnetospheres, scientists infer properties of planetary interiors that cannot be measured directly. Magnetic fields also evolve. Earth's field has weakened and strengthened many times. Polarity reversals occur irregularly. Jupiter's field may change as its interior cools. Saturn's helium rain may alter convection patterns. Uranus and Neptune may see shifts as their mantles evolve. Magnetic fields are living features, tied to the slow changes unfolding below. This connection makes magnetic fields powerful diagnostic tools. They provide real-time evidence that something inside a planet is moving. When combined with gravity data, seismic measurements, and laboratory experiments, magnetic observations help constrain interior models and eliminate possibilities. There is also a broader implication. When scientists search for habitable worlds beyond the solar system, magnetic fields become part of the discussion. A planet with a long-lived magnetic field is more likely to retain an atmosphere over billions of years. It is more likely to protect surface conditions from stellar winds. Interior motion becomes indirectly linked to surface habitability. This does not mean a magnetic field guarantees life, but it does indicate a planet whose interior remains active, whose heat has not yet faded, and whose surface may be buffered from some of the harsher aspects of space. Magnetic fields therefore tie together many themes. They connect heat to motion, motion to electricity, electricity to space, and space back to atmosphere and surface. They are bridges between the deep interior and the environment far beyond the planet itself. In the end, a magnetic field is a whisper from the inside. It tells of molten layers, convecting fluids, and energy still flowing upward. When that whisper fades, it signals that the interior has quieted and the planet has entered a different chapter of its long history. Across the solar system, magnetic fields trace the invisible dance of moving interiors, revealing which worlds are still alive beneath the surface and which have settled into silence. A planet is never finished. From the moment it forms, its interior begins a long, irreversible journey of change. Heat leaks away, materials shift phase, motion slows. What begins as a hot, restless body gradually settles into something quieter. This evolution happens so slowly that it is invisible on human timescales, yet it governs everything a planet can become. The fundamental driver of interior change is cooling. All planets begin warm. Accretion releases energy, impacts deliver heat. Radioactive elements add internal warmth, but no planet generates infinite energy. From the first moment onward, heat begins to escape into space. The only questions are how fast it escapes and what happens along the way. Cooling is not uniform. Heat leaves a planet primarily through its surface, radiating outward. The interior cools from the outside in. This creates temperature gradients that drive motion. Hot material rises, cooler material sinks. As long as these gradients exist, convection can continue. Once they weaken, motion slows. The rate at which a planet cools depends strongly on size. Large planets lose heat slowly because their volume grows faster than their surface area. Small planets lose heat quickly. This simple geometric relationship underlies much of planetary diversity. Earth remains active because it is large enough to retain heat. The Moon cooled rapidly because it is small. Mars sits in between, lingering in a transitional state before settling down. As planets cool, materials change phase. Molten regions begin to crystallize. Liquids become solids. In rocky mantles, minerals rearrange into denser crystal structures. In metallic cores, iron solidifies from the inside outward as pressure and temperature conditions change. These phase changes are not passive. They release or absorb heat, altering the planet's thermal balance. Crystallization can prolong activity. When a liquid core begins to solidify, it releases latent heat. Lighter elements are expelled into the remaining liquid, increasing buoyancy and driving convection. This process helps sustain magnetic fields on planets like Earth. The growth of the inner core is therefore not just a consequence of cooling, but an active participant in interior evolution. Eventually, however, cooling wins. As heat production declines and temperature gradients flatten, convection weakens. Mantles become more rigid, cores solidify, magnetic fields fade, geological activity declines. This progression is not identical for every planet, but the direction is the same. To understand these changes, scientists use thermal evolution models. These models track how heat moves through a planet over time. They account for heat sources such as radioactive decay, residual formation energy, and phase transitions. They include mechanisms of heat transport such as conduction, convection, and radiation. By adjusting parameters like size, composition, and initial temperature, scientists simulate different evolutionary paths. These models reveal why planets diverge. Two planets with similar compositions can age very differently if one loses heat faster or transports it less efficiently. A planet with plate tectonics can shed heat steadily and remain active for long periods. A planet with a stagnant lid may trap heat, leading to episodic activity or long-term insulation. A planet with strong compositional layering may suppress convection altogether. Interior change is therefore not just about cooling, but about how cooling happens. The consequences extend far beyond geology. Interior evolution shapes atmospheres. Volcanism releases gases that build atmospheres. Magnetic fields protect those atmospheres from erosion. Tectonics recycle carbon and regulate climate. When interior activity declines, these surface processes change or stop. This creates a link between deep interiors and habitability. On Earth, long-lived interior motion supports a stable climate over billions of years. On Mars, early interior activity allowed liquid water, but its loss led to atmospheric collapse. On Venus, interior heat combined with the lack of plate tectonics contributed to runaway greenhouse conditions. The same internal processes can support or undermine habitability, depending on how they unfold. Planetary aging therefore follows multiple paths. Some planets cool quickly and become inert early. Others maintain activity for billions of years. Some experience long, quiet periods punctuated by catastrophic resurfacing. Some evolve smoothly. The outcome depends on size, composition, early history, and chance events such as major impacts. These divergent paths are visible across the solar system. Mercury shrank as its oversized core cooled. The Moon froze early and preserved ancient history. Mars lost its magnetic field and atmosphere. Earth remained active. Venus trapped its heat beneath a rigid shell. Jupiter and Saturn continue to radiate energy from deep interiors. Uranus cooled quietly. Neptune retained its heat against expectation. Each world tells a different aging story. Despite this diversity, certain trends are universal. Heat always flows outward. Motion always slows eventually. No planet remains young forever. Even gas giants will one day exhaust their internal energy, their storms fading as equilibrium is reached. The timescales involved are immense. Interior evolution unfolds over hundreds of millions to billions of years. Changes that determine a planet's fate may be decided early, but their consequences play out slowly. A slight difference in early heat content can echo across geological time. This perspective reshapes how planets are viewed. Rather than static objects, planets are processes. Their interiors are engines that run down gradually, shaping surfaces, atmospheres, and magnetic fields as they go. What is seen at any given moment is a snapshot taken mid-journey. Understanding interior change also reframes comparisons. Earth is not a default planet. It is one outcome among many. Its long-lived activity is contingent, not guaranteed. Studying other worlds reveals how easily different paths could have been taken. This has implications beyond the solar system. When astronomers observe distant planets, they often see only mass, size, and orbit. Inferring habitability or activity requires assumptions about interior evolution. Thermal models built from solar system examples provide the framework for those inferences. Interior change therefore connects local observations to cosmic questions. It links the early chaos of planet formation to the quiet stability or hostility of mature worlds. It explains why some planets remain dynamic while others become fossils. It shows how time itself is a shaping force. In the end, every planet carries the memory of its heat. As that memory fades, so too does motion, magnetism, and renewal. What remains is a record written into rock, atmosphere, and orbit, shaped by a deep interior that once burned brighter than it ever could again. Planetary interiors change slowly, but they change everything. When all the planets are placed side by side, their differences can seem overwhelming. Some are small and dense, others vast and diffuse. Some are rocky, others gaseous, others dominated by exotic mixtures of water, ammonia, and methane. Yet beneath this variety lies a coherent pattern. Planetary interiors follow the same physical laws, even though those laws express themselves in dramatically different ways. The most fundamental divide is between rocky planets and giant planets. Rocky planets are built primarily from silicate rock and metal. Their interiors are defined by solid crusts, convecting mantles, and metallic cores. Heat moves slowly through rock, and once it is lost, it is difficult to replace. This makes rocky planets sensitive to size. A small rocky body cools quickly and becomes inert. A larger one retains heat longer and can remain active for billions of years. Gas giants operate in a different regime. Jupiter and Saturn are dominated by hydrogen and helium. Their immense mass compresses these light elements into dense conductive states. Heat transport is efficient. Convection is vigorous. Instead of rigid shells and creeping rock, their interiors behave as deep, slowly churning fluids. These planets retain enormous amounts of internal energy, not only from formation, but also from ongoing gravitational contraction. Ice giants occupy a middle ground. Uranus and Neptune contain significant amounts of rock and metal, but their defining layers are rich in volatile compounds. Their mantles are composed of dense, hot fluids rather than solid rock or metallic hydrogen. Heat transport in these environments depends sensitively on composition and layering, leading to outcomes that are surprisingly divergent even between similar planets. Across all these categories, mass plays a central role. More massive planets retain heat longer because their volume increases faster than their surface area. This simple scaling law explains why Jupiter remains internally active while the Moon does not. It also explains why Mars lingered in an intermediate state, active early but unable to sustain that activity indefinitely. Heat retention, however, is not the whole story. How heat moves matters just as much as how much heat there is. A planet with efficient convection can shed heat steadily and remain active. A planet with suppressed convection may trap heat beneath a rigid shell, leading to episodic or uneven activity. Composition, phase changes, and internal layering all influence this behavior. This is why no two planets evolve identically. Even when planets begin with similar ingredients, small differences in size, composition, or early history can lead to divergent paths. Venus and Earth began with comparable masses and materials, yet one developed mobile plates and long-term climate regulation while the other did not. Uranus and Neptune are similar in size, yet one appears insulated and quiet, while the other radiates heat vigorously. Formation location adds another layer of variation. Planets that formed close to the Sun incorporated different materials than those that formed farther out. High temperatures in the inner solar system favoured metal and rock. Cooler conditions beyond the frost line allowed water, ammonia, and methane to condense and become major components. These initial differences set the stage for everything that followed. Early timing also mattered. Planets that formed quickly captured short-lived radioactive heat sources and differentiated early. Those that formed later missed this window and remained colder. Impacts added randomness, redistributing heat and material in ways that could permanently alter interior structure. A single collision could tilt a planet, mix its layers, or strip away part of its mantle. Despite this complexity, certain themes repeat. Differentiation appears wherever melting occurs. Dense materials sink, lighter materials rise, layers form. Once layered, planets develop characteristic modes of heat transport and magnetic field generation. As interiors cool, motion slows, magnetic fields weaken, geological activity declines. The rocky planets illustrate this progression clearly. Mercury's oversized core cooled and contracted, reshaping its surface. The Moon froze early and preserved ancient history. Mars lost its magnetic field and atmosphere as its interior cooled. Earth retained heat long enough to sustain tectonics and a magnetic field into the present day. The giant planets show a different version of the same story. Jupiter and Saturn remain active because their mass keeps their interiors warm and mobile. Uranus and Neptune diverged, one becoming quiet, the other remaining energetic, likely due to differences in internal structure and heat transport rather than size alone. Asteroids fill in the smallest scale, some differentiated briefly and then froze, exposing their interiors through collisions. Others never melted at all. Together they show that interior evolution is not exclusive to large worlds. It begins wherever heat and gravity are sufficient, even if only temporarily. When viewed as a system, the solar system's planets form a continuum. They span a range of masses, compositions, and thermal histories, but they are connected by shared physics. Gravity compresses, heat flows, materials respond. The outcomes vary, but the rules do not. This system-wide perspective reveals an important truth. There is no single planetary interior blueprint. There is no standard outcome. Each planet represents a solution to the same equations under different boundary conditions. Change the mass slightly, adjust the composition, alter the timing, the solution shifts. This understanding reshapes how planets are compared. Earth is not typical or inevitable. It is one expression among many. Its long-lived activity reflects a balance that could easily have tipped another way. Studying other planets does not diminish Earth's uniqueness, it explains it. The same perspective extends beyond the solar system. Exoplanets discovered around other stars span masses and compositions that overlap with all the categories seen here and extend beyond them. Understanding how interiors behave across the solar system provides the foundation for interpreting those distant worlds. Without this comparative framework, mass and radius measurements would be little more than numbers. Planetary interiors are therefore not isolated topics. They connect formation to evolution, deep interiors to surface conditions, and local observations to cosmic patterns. They reveal how diversity emerges from shared rules. When all planetary interiors are compared, the message is clear. Difference is the norm. Similarity is contextual. Each planet carries the imprint of its mass, its materials, its birth environment, and its history. Those imprints are written deep inside, long before surfaces form and long before atmospheres settle. To compare planetary interiors is to see the solar system not as a collection of objects, but as a set of experiments run in parallel. Each planet explores a different path through the same physical landscape. Some remain active, some fade quickly, some surprise, all obey the same laws, and together they show that what lies inside a planet matters as much as where it orbits or how it looks from afar. Even after centuries of observation and decades of spacecraft exploration, much of what lies beneath the planets remains uncertain. This is not because the questions are poorly framed or the tools are crude, but because planetary interiors occupy regimes that are fundamentally difficult to access. They exist at pressures, temperatures, and scales that resist direct measurement, forcing science to proceed carefully, one inference at a time. The most basic limitation is distance. No probe has ever reached a planetary core. No drill has penetrated more than a tiny fraction of a rocky planet's crust. Everything known about deeper layers comes from indirect signals, gravity fields, magnetic measurements, seismic waves where available, and laboratory experiments conducted on microscopic samples must stand in for direct observation. Each method reveals something real, but none provides a complete picture. Gravity data, for example, can reveal how mass is distributed inside a planet, but it cannot uniquely determine composition. Different internal arrangements can produce similar gravity signatures. A dense core with a light mantle may look similar to a more diffuse distribution of heavy elements, spread over a larger region. Models must therefore rely on assumptions grounded in chemistry, formation theory, and comparison with other planets. When those assumptions shift, interpretations shift with them. Magnetic fields present similar challenges. They reveal the presence of electrically conductive motion, but not its exact location or composition. A magnetic field tells scientists that something inside is moving and conducting electricity. It does not specify whether that motion occurs in molten iron, metallic hydrogen, or exotic ionic fluids. Multiple interior structures can generate similar magnetic behavior. Seismology offers the most direct interior constraints, but only for a few worlds. Earth's interior is mapped in remarkable detail because seismic waves crisscross the planet continuously. Mars has provided a first glimpse through the InSight mission, but coverage was limited in time and location. The Moon offered early seismic data through Apollo experiments, but with sparse instrumentation. For other planets, seismology remains out of reach for now. Even when seismic data exist, interpretation is not straightforward. Wave speeds depend on temperature, composition, pressure, and crystal structure. Untangling these effects requires laboratory measurements and theoretical models, both of which introduce uncertainty. Small changes in assumed composition can alter inferred temperatures or layer boundaries significantly. Laboratory experiments themselves face limits. Recreating planetary interior conditions requires compressing tiny samples to enormous pressures for very short times. Diamond anvil cells and laser-driven shocks provide invaluable data, but they cannot perfectly replicate the slow, sustained conditions inside planets. Scaling results from microscopic samples to planetary volumes requires careful modeling and extrapolation. Theoretical models fill in the gaps, but they too are incomplete. Equations describing heat flow, convection, and phase transitions are well established. Yet they depend on material properties that are not always known precisely. Viscosity, conductivity, and phase boundaries can vary dramatically under extreme conditions. When these parameters are uncertain, models produce ranges of outcomes rather than single answers. This is why core structures remain debated. Does Jupiter have a compact core or a diffuse one? How sharply defined are the boundaries between layers? How much heavy material is mixed into metallic hydrogen? Similar questions apply to Saturn, Uranus, and Neptune, where limited data allow multiple interpretations. Phase behavior introduces another layer of uncertainty. Water, ammonia, methane, and hydrogen behave in unfamiliar ways under extreme pressure. Superionic phases, phase separation, and chemical breakdown are active areas of research. Small shifts in pressure or temperature can change which phases are stable, altering density and conductivity in ways that affect convection and magnetic field generation. Some uncertainties persist because they unfold over immense timescales. Interior evolution happens over billions of years. Direct observation captures only a moment. Models must reconstruct histories based on present conditions and plausible starting points. Different histories can converge on similar present states, making it difficult to know which path was taken. Early events are especially hard to reconstruct. Giant impacts, rapid accretion phases, and early radioactive heating shaped planetary interiors profoundly. Evidence of these events is often erased or buried. What remains are indirect clues, interpreted through models that cannot be fully validated. Despite these challenges, progress continues. Future missions promise new data. Proposed orbiters and probes could measure gravity and magnetic fields with greater precision. Atmospheric entry probes may sample composition more deeply, constraining interior models indirectly. Seismic experiments on other planets remain a long-term goal. Advances in laboratory physics will also matter. As experimental techniques improve, scientists will better constrain the behavior of materials under planetary conditions. Improved measurements of conductivity, viscosity, and phase transitions will sharpen models and reduce uncertainty. Computational power plays a role as well. More detailed simulations allow researchers to explore a wider range of interior structures and evolutionary paths. Rather than seeking a single answer, science increasingly maps the space of possibilities, identifying which scenarios are consistent with all available data. It is important to recognize that uncertainty is not ignorance. What remains unknown exists at the frontier between evidence and inference. Each uncertainty is bounded, informed by physics, and constrained by observation. The unknowns are specific, not vague. They define where understanding is still incomplete rather than undermining what is known. In this way, planetary interiors are both understood and mysterious. Their broad structures are clear. Their governing principles are well established. Their details, however, resist final resolution. This balance between knowledge and uncertainty is characteristic of mature science operating at extreme limits. There is also a philosophical dimension. Planetary interiors remind us that not all truths are directly observable. Some must be inferred patiently, pieced together from subtle effects and partial signals. Understanding emerges gradually, not through dramatic discovery, but through accumulation and refinement. As exploration continues, some mysteries will narrow. Others may persist indefinitely, constrained not by lack of curiosity or effort, but by the fundamental difficulty of probing worlds at scales and conditions beyond direct reach. This does not diminish their value. It defines their character. What remains unknown beneath the planets is not a void. It is a carefully mapped region of uncertainty, shaped by evidence, bounded by physics, and steadily shrinking as new data arrive. It is where future discoveries will occur, not because current knowledge has failed, but because it has advanced far enough to reveal the next set of questions. Beneath the planets, much is known, much is inferred, and some things remain unresolved. That balance is not a flaw. It is the natural state of understanding at the edge of the observable universe. Every planet appears calm from a distance. Even the most violent storms, the deepest canyons, and the brightest rings exist only at the surface, forming a thin boundary between space and something far larger below. Beneath that boundary, hidden from view, lie interiors that decide how planets move, age, and ultimately become what they are. Throughout this journey inward, a consistent pattern emerges. Surfaces respond, interiors decide. Mountains rise because mantles move. Atmospheres persist or vanish because magnetic fields live or die. Oceans appear or disappear because heat either flows steadily or becomes trapped. Even a planet's shape, tilt, and rhythm are written by slow processes unfolding far below anything that can be photographed. What makes this remarkable is how little of it can be seen directly. Planetary interiors are known through whispers rather than images, through gravity tugging gently on spacecraft, through magnetic fields bending invisible particles, through seismic waves trembling briefly across distant ground, through fragments of ancient bodies that fall to Earth as meteorites, carrying pieces of lost worlds in their structure. From these faint signals, coherent stories emerge. They reveal that planets are not static objects but evolving systems, born hot and restless. They cool, crystallize, and settle over immense spans of time. Some lose their heat quickly and fall silent early. Others retain internal motion for billions of years. A few remain active far longer than intuition would suggest. Size matters, but it is never the whole explanation. Composition shapes how heat moves. Early history sets paths that cannot easily be reversed. Chance events, such as impacts or timing differences in formation, leave permanent marks. Two planets can begin with similar ingredients and diverge completely, guided by differences hidden deep inside. This diversity is not chaos. It is the natural outcome of the same physical laws playing out under different conditions. Gravity compresses, heat flows outward, materials separate by density, motion emerges where energy allows it. These principles apply everywhere, from the smallest asteroid to the largest gas giant. The quiet truth is that most of a planet's life happens slowly. Interiors change over millions and billions of years. Heat leaks away patiently. Magnetic fields fade gradually. Geological activity declines step by step. These processes rarely announce themselves dramatically. They shape outcomes long before those outcomes become visible. In this way, planetary interiors connect deep time to the present. They link the violence of early formation to the calm stability or hostility of mature worlds. They explain why some planets preserve ancient scars while others erase their past. They show how long-term habitability, or its absence, is rooted in processes far beneath the surface. They also expand perspective beyond familiar ground. Earth's interior feels normal only because it is home. Seen alongside other worlds, it becomes one possibility among many. Its long-lived activity is neither guaranteed nor universal. It is the result of a particular balance between size, composition, heat, and time. The same is true elsewhere. Mercury's metal-heavy heart reshaped its surface. Venus's locked interior trapped its heat. Mars's cooling silenced its dynamo. The Moon froze early and remembered everything. Jupiter and Saturn continue to glow from within. Uranus turned quiet. Neptune defied expectation. Each world tells a different interior story, written beneath familiar skies. And beyond the solar system, countless other planets are doing the same. Worlds larger, smaller, denser, stranger, many unseen, many unimagined, all shaped from the inside out. What lies beneath the surface of a planet is not merely structure, it is history. It is the slow accumulation of decisions made by physics, chemistry, and time. Decisions that cannot be undone, only carried forward. In the end, planets are not defined by how they look, but by how they behave over time. And that behavior begins in darkness, under pressure, beneath layers that never see the light. The worlds we observe are quiet on the outside, and the worlds beneath are anything but.